An image shows four sets of medical pictures. The first is the torso and arms of a human skeleton with purple shading in the muscular regions. The second is a set of four images. The top left, labeled smoker, shows an oval-shaped image that is blue on the outside rim, green as you move inward, and bright red near the center, while the top right, labeled non-smoker, shows an oval-shaped image that is shaded bright green over most of the image and bright red near the center. The lower left image of the four, labeled alcoholic, shows an oval-shaped image that is almost entirely blue with two small yellow-rimmed red dots near the upper middle section, while the lower right image, labeled normal, looks very similar to the lower left, but the red regions are slightly larger. The final image shows two scans of a human torso that is turned to face to the side. The left scan has three bright yellow-white areas, one in the throat, one in the chest, and one in the head. The right scan is the same as the left, except the bright regions are dim and the internal organs are more clearly defined. Figure 21. One nuclear chemistry provides the basis for many useful diagnostic and therapeutic methods in medicine, such as these positron emission tomography, PET scans. The PET computed tomography scan on the left shows muscle activity. The brain scans in the center show chemical differences in dopamine signaling in the brains of addicts and non-addicts. The images on the right show an oncological application of PET scans to identify lymph node metastasis. Chapter outline. 21. One nuclear structure and stability. 21. Two nuclear equations. 21. 3 radioactive decay. 21. 4 transmutation and nuclear energy. 21. 5 uses of radioisotopes. 21. 6 biological effects of radiation. The chemical reactions that we have considered in previous chapters involve changes in the electronic structure of the species involved. That is, the arrangement of the electrons around atoms, ions, or molecules. Nuclear structure. The numbers of protons and neutrons within the nuclei of the atoms involved remains unchanged during chemical reactions. This chapter will introduce the topic of nuclear chemistry, which began with the discovery of radioactivity in 1896 by French physicist Antoine Becquerel, and has become increasingly important during the 20th and 21st centuries, providing the basis for various technologies related to energy, medicine, geology, and many other areas. Learning objectives. By the end of this section, you will be able to describe nuclear structure in terms of protons, neutrons, and electrons. Calculate mass defect and binding energy for nuclei. Explain trends in the relative stability of nuclei. Nuclear chemistry is the study of reactions that involve changes in nuclear structure. The chapter on atoms, molecules, and ions introduced the basic idea of nuclear structure, that the nucleus of an atom is composed of protons, and with the exception of 11H, neutrons. Recall that the number of protons in the nucleus is called the atomic number, Z, of the element, and the sum of the number of protons and the number of neutrons is the mass number, A. Atoms with the same atomic number but different mass numbers are isotopes of the same element. When referring to a single type of nucleus, we often use the term nuclide and identify it by the notation AZX, where X is the symbol for the element, A is the mass number, and Z is the atomic number, for example, 146C. Often a nuclide is referenced by the name of the element followed by a hyphen and the mass number. For example, 146C is called carbon-14. Protons and neutrons, collectively called nucleons, are packed together tightly in a nucleus. With a radius of about 10-15 meters, a nucleus is quite small compared to the radius of the entire atom, which is about 10-10 meters. Nuclei are extremely dense compared to bulk matter, averaging 1.8 times 10-14 grams per cubic centimeter. For example, water has a density of 1 gram per cubic centimeter, and iridium, one of the densest elements known, has a density of 22.6 g/cm3. If the Earth's density were equal to the average nuclear density, the Earth's radius would be only about 200 meters. Earth's actual radius is approximately 6.4 times 106 meters, 30,000 times larger. Example 21. 1 demonstrates just how great nuclear densities can be in the natural world. Example 21. 1. Density of a neutron star. Neutron stars form when the core of a very massive star undergoes gravitational collapse, causing the star's outer layers to explode in a supernova. Composed almost completely of neutrons, they are the densest known stars in the universe, with densities comparable to the average density of an atomic nucleus. A neutron star in a faraway galaxy has a mass equal to 2.4 solar masses. 1 solar mass equals m equals mass of the Sun equals 199 times 1030 kg and a diameter of 26 km. A. What is the density of this neutron star? B. How does this neutron star's density compare to the density of a uranium nucleus, which has a diameter of about 15 fm? 1 fm equals 1015 m. Solution. We can treat both the neutron star and the U-235 nucleus as spheres. Then the density for both is given by letter 1d451 equals letter 1d45a, letter 1d449 with letter 1d449 equals 43, letter 1d70b, letter 1d45f3. A. The radius of the neutron star is 12 times 26 km equals 12 times 2. 6 times 104 m equals 1. 3 times 104 m. So the density of the neutron star is letter 1d451 equals letter 1d45a, letter 1d449 equals letter 1d45a, 43, letter 1d70b, letter 1d45f, 3 equals 2. 4, 1. 99 times 1030 kg, 43, letter 1d70b, 1. 3 times 104 m3 equals 5. 2 times 1017 kg/m3. B. The radius of the U-235 nucleus is 12 times 15 times 10 minus 15 m equals 7. 5 times 10 minus 15 m. So the density of the U-235 nucleus is letter 1d451 equals letter 1d45a, letter 1d449 equals letter 1d45a, 43, letter 1d70b, letter 1d45f, 3 equals 235 AMU, 1. 66 times 10 minus 27 kg, 1, AMU 43, letter 1d70b, 7. 5 times 10 minus 15 m3 equals 2. 2 times 1017 kg/m3. These values are fairly similar, same order of magnitude. But the neutron star is more than twice as dense as the U-235 nucleus. Check your learning. Find the density of a neutron star with a mass of 197 solar masses and a diameter of 13 km, and compare it to the density of a hydrogen nucleus, which has a diameter of 1.75 fm. 1 fm equals 1 times 1015 m. Answer. The density of the neutron star is 3-4 times 1018 kg/m3. The density of a hydrogen nucleus is 6 times 1017 kg/m3. The neutron star is 5-7 times denser than the hydrogen nucleus. To hold positively charged protons together in the very small volume of a nucleus requires very strong attractive forces because the positively charged protons repel one another strongly at such short distances. The force of attraction that holds the nucleus together is the strong nuclear force. The strong force is one of the 4 fundamental forces that are known to exist. The others are the electromagnetic force, the gravitational force, and the nuclear weak force. This force acts between protons, between neutrons, and between protons and neutrons. It is very different from the electrostatic force that holds negatively charged electrons around a positively charged nucleus, the attraction between opposite charges. Over distances less than 10-15 meters, and within the nucleus, the strong nuclear force is much stronger than electrostatic repulsions between protons. Over larger distances and outside the nucleus, it is essentially non-existent. Link to learning. Visit this website for more information about the 4 fundamental forces. Nuclear binding energy. As a simple example of the energy associated with the strong nuclear force, consider the helium atom composed of 2 protons, 2 neutrons, and 2 electrons. The total mass of these 6 subatomic particles may be calculated as 2 times 1, 73 AMU plus protons 2 times 1, 87 AMU plus neutrons 2 times 0, 55 AMU equals electrons 4, 331 AMU. However, mass spectrometric measurements reveal that the mass of an 42 He atom is 4.26 AMU, less than the combined masses of its 6 constituent subatomic particles. This difference between the calculated and experimentally measured masses is known as the mass defect of the atom. In the case of helium, the mass defect indicates a loss in mass of 4,331 AMU, 426 AMU equals 0.305 AMU. The loss in mass accompanying the formation of an atom from protons, neutrons, and electrons is due to the conversion of that mass into energy that is evolved as the atom forms. The nuclear binding energy is the energy produced when the atoms, nucleons, are bound together. This is also the energy needed to break a nucleus into its constituent protons and neutrons. In comparison to chemical bond energies, nuclear binding energies are vastly greater, as we will learn in this section. Consequently, the energy changes associated with nuclear reactions are vastly greater than are those for chemical reactions. The conversion between mass and energy is most identifiably represented by the mass-energy equivalence equation, as stated by Albert Einstein. Letter 1d438 equals letter 1d450 letter 1d450, 2, where E is energy, m is mass of the matter being converted, and c is the speed of light in a vacuum. This equation can be used to find the amount of energy that results when matter is converted into energy. Using this mass-energy equivalence equation, the nuclear binding energy of a nucleus may be calculated from its mass defect, as demonstrated in example 21. 2. A variety of units are commonly used for nuclear binding energies, including electron volts, eV, with 1 eV equaling the amount of energy necessary to move the charge of an electron across an electric potential difference of 1 volt, making 1 eV equals 1.602 times 1019 J. Example 21. 2. Calculation of nuclear binding energy. Determine the binding energy for the nuclide 42 He in A. Joules per mole of nuclei, B. Joules per nucleus, C. MeV per nucleus. Solution. The mass defect for a 42 He nucleus is 0.305 AMU as shown previously. Determine the binding energy in joules per nuclide using the mass-energy equivalence equation. To accommodate the requested energy units, the mass defect must be expressed in kilograms. Recall that 1J equals 1 kg m2s2. First, express the mass defect in G/mol. This is easily done considering the numerical equivalence of atomic mass AMU and molar mass G/mol that results from the definitions of the AMU and mole units. Refer to the previous discussion in the chapter on atoms, molecules, and ions if needed. The mass defect is therefore 0.305 G/mol. To accommodate the units of the other terms in the mass-energy equation, the mass must be expressed in kg, since 1J equals 1 kg m2s2. Converting grams into kilograms yields a mass defect of 3.5 times 10⁵ kg/mol. Substituting this quantity into the mass-energy equivalence equation yields Letter 1D438 equals letter 1D450 letter 1D450 2 equals 3. 0, 5 times 10 minus 5 kg mol times 2. 998 times 108 ms 2 equals 2. 74 times 1012 kg to s minus 2 mol minus 1 equals 2. 74 times 1012 j mol minus 1 equals 2. 74 tj mol minus 1. Note that this tremendous amount of energy is associated with the conversion of a very small amount of matter, about 30 mg, roughly the mass of typical drop of water. B. The binding energy for a single nucleus is computed from the molar binding energy using Avogadro's number. Letter 1D438 equals 2. 74 times 1012 j mol minus 1 times 1 mol 6. Nuclei, 55 times 10 minus 12 j equals 4, 55 pj. C. Recall that 1 EV equals 1. 602 times 1019 j using the binding energy computed in Part B. Letter 1D438 equals 4. 55 times 10 minus 12 j times 1 EV1. 602 times 10 minus 19 j equals 2. 84 times 107 EV equals 28. 4 MeV. Check your learning. What is the binding energy for the nuclide 199F? Atomic mass, 1899-84 AMU in MeV per nucleus. Answer, 148.4 MeV. Because the energy changes for breaking and forming bonds are so small compared to the energy changes for breaking or forming nuclei, the changes in mass during all ordinary chemical reactions are virtually undetectable. As described in the chapter on thermochemistry, the most energetic chemical reactions exhibit enthalpies on the order of thousands of kJ/mol, which is equivalent to mass differences in the nanogram range, 10^9 G. On the other hand, nuclear binding energies are typically on the order of billions of kJ/mol, corresponding to mass differences in the milligram range, 10^3 G. Nuclear stability. A nucleus is stable if it cannot be transformed into another configuration without adding energy from the outside. Of the thousands of nuclides that exist, about 250 are stable. A plot of the number of neutrons versus the number of protons for stable nuclei reveals that the stable isotopes fall into a narrow band. This region is known as the band of stability, also called the belt, zone, or valley of stability. The straight line in Figure 21.2 represents nuclei that have a 1:1 ratio of protons to neutrons N/P ratio. Note that the lighter stable nuclei in general have equal numbers of protons and neutrons. For example, nitrogen-14 has 7 protons and 7 neutrons. Heavier stable nuclei, however, have increasingly more neutrons than protons. For example, iron-56 has 30 neutrons and 26 protons, an N/P ratio of 1:15, whereas the stable nuclide lead-2O7 has 125 neutrons and 82 protons, an N/P ratio equal to 1:52. This is because larger nuclei have more proton-proton repulsions and require larger numbers of neutrons to provide compensating strong forces to overcome these electrostatic repulsions and hold the nucleus together. A graph is shown where the x-axis is labeled number of neutrons, open parenthesis, n, close parenthesis, and has values of 0 to 180 in increments of 10. The y-axis is labeled number of protons, open parenthesis, z, close parenthesis, and has values of 0 to 120 in increments of 10. A green shaded band of varying width, labeled radioactive, extends from point 0 on both axes to 178 on the y-axis and 118 on the x-axis in a linear manner. The width of this band varies from 8 to 18 units in width, according to the x-axis measurements. A blue line in a roughly zigzag pattern runs through the middle of the shaded band and stops at 128 on the y-axis and 82 on the x-axis. This line is labeled non-radioactive. An unlabeled black solid line extends from point 0, 0 to 120, 120 in a linear manner. Figure 21. 2. This plot shows the nuclides that are known to exist and those that are stable. The stable nuclides are indicated in blue, and the unstable nuclides are indicated in green. Note that all isotopes of elements with atomic numbers greater than 83 are unstable. The solid line is the line where N equals Z. The nuclei that are to the left or to the right of the band of stability are unstable and exhibit radioactivity. They change spontaneously, decay, into other nuclei that are either in or closer to the band of stability. These nuclear decay reactions convert one unstable isotope or radioisotope into another, more stable isotope. We will discuss the nature and products of this radioactive decay in subsequent sections of this chapter. Several observations may be made regarding the relationship between the stability of a nucleus and its structure. Nuclei with even numbers of protons, neutrons, or both are more likely to be stable. See Table 21. 1. Nuclei with certain numbers of nucleons, known as magic numbers, are stable against nuclear decay. These numbers of protons or neutrons, 2, 8, 20, 28, 50, 82, and 126, make complete shells in the nucleus. These are similar in concept to the stable electron shells observed for the noble gases. Nuclei that have magic numbers of both protons and neutrons, such as 42 He, 168 O, 4020 Ka, and 20,882 Pb, are called double magic and are particularly stable. These trends in nuclear stability may be rationalized by considering a quantum mechanical model of nuclear energy states analogous to that used to describe electronic states earlier in this textbook. The details of this model are beyond the scope of this chapter. Stable nuclear isotopes. Number of stable isotopes, proton number, neutron number. 150, 7 even, 53 even odd, 50 odd even, 5 odd. Table 21. 1. The relative stability of a nucleus is correlated with its binding energy per nucleon, the total binding energy for the nucleus divided by the number or nucleons in the nucleus. For instance, we saw in example 21, 2, that the binding energy for a 42 He nucleus is 28. For MeV, the binding energy per nucleon for a 42 He nucleus is therefore 28. For MeV, 4 nucleons equals 7. 10 MeV nucleon. In example 21, 3, we learn how to calculate the binding energy per nucleon of a nuclide on the curve shown in figure 21. 3. A graph is shown where the x-axis is labeled binding energy per nucleon, open parenthesis, MeV, close parenthesis, and has values of 0 to 10 in increments of 1. The y-axis is labeled mass number and has values of 0 to 260 in increments of 20. A line of best fit beginning at point 0, 0 is drawn through points 8, 5, 5, 9, 7, 3, 18, 7, 1, 20, 7, 5, 19, 7, 9, 27, 7, 8, 21, 8, 1, 25, 8, 4, 37, 8, 6, 43, 8, 8, 57, 8, 6, 60, 8, 9, 79, 88, 8, 8, 102, 8, 9, 108, 8, 5, 126, 8, 7, 133, 8, 8, 143, 8, 2, 157, 8, 1, 167, 8, 2, 195, 7, 9, 205, 7, 9, 241, 7, 3, and 255, 75. An upward-facing arrow near the bottom left of the graph is labeled fusion, while a left-facing arrow near the top right is labeled fission. Figure 21. 3. The binding energy per nucleon is largest for nuclides with mass number of approximately 56. Example 21. 3. Calculation of binding energy per nucleon. The iron nuclide 5626 Phe lies near the top of the binding energy curve, figure 21.3, and is one of the most stable nuclides. What is the binding energy per nucleon in MeV for the nuclide 5626 Phe? Atomic mass of 55, 9349 AMU. Solution. As in example 21. 2. We first determine the mass defect of the nuclide, which is the difference between the mass of 26 protons, 30 neutrons, and 26 electrons, and the observed mass of an 5626 Phe. Atom. Mass defect equals 26 times 1, 73 AMU plus 30 times 1, 87 AMU plus 26 times 0, 55 AMU minus 55. 9349 AMU equals 56, 4651 AMU minus 55, 9349 AMU equals 0, 5302 AMU. We next calculate the binding energy for one nucleus from the mass defect using the mass-energy equivalence equation. Letter 1D438 equals letter 1D458 letter 1D4502 equals 0, 5302 AMU times 1. 6,605 times 10 minus 27 kg 1 AMU times 2. 998 times 108 m slash S2 equals 7. 913 times 10 minus 11 kg m slash S2 equals 7. 913 times 10 minus 11 J. We then convert the binding energy in joules per nucleus into units of MeV per nuclide. 913 times 10 minus 11 J times 1 MeV1. 602 times 10 minus 13 J equals 493, 9 MeV. Finally, we determine the binding energy per nucleon by dividing the total nuclear binding energy by the number of nucleons in the atom. Binding energy per nucleon equals 493, 9 MeV56 equals 8. 820 MeV nucleon. Note that this is almost 25% larger than the binding energy per nucleon for 42 He. Note also that this is the same process as in example 21.1, but with the additional step of dividing the total nuclear binding energy by the number of nucleons. Check your learning. What is the binding energy per nucleon in 199F? Atomic mass 1899-84 AMU. Answer 7810 MeV nucleon. Learning objectives. By the end of this section, you will be able to identify common particles and energies involved in nuclear reactions, write and balance nuclear equations, changes of nuclei that result in changes in their atomic numbers, mass numbers, or energy states are nuclear reactions. To describe a nuclear reaction, we use an equation that identifies the nuclides involved in the reaction, their mass numbers and atomic numbers, and the other particles involved in the reaction. Types of particles in nuclear reactions. Many entities can be involved in nuclear reactions. The most common are protons, neutrons, alpha particles, beta particles, positrons, and gamma rays, as shown in figure 21. For protons 11p, also represented by the symbol 11H, and neutrons 10N, are the constituents of atomic nuclei and have been described previously. Alpha particles 42 He, also represented by the symbol 42 alpha, are high-energy helium nuclei. Beta particles 0-1 beta, also represented by the symbol 0-1 E, are high-energy electrons, and gamma rays are photons of very high-energy electromagnetic radiation. Positrons 0+1 E, also represented by the symbol +1 beta, are positively charged electrons, anti-electrons. The subscripts and superscripts are necessary for balancing nuclear equations, but are usually optional in other circumstances. For example, an alpha particle is a helium nucleus He, with a charge of +2 and a mass number of 4, so it is symbolized 42 He. This works because, In general, the ion charge is not important in the balancing of nuclear equations. This table has 4 columns and 7 rows. The first row is a header row and it labels each column: name, symbol S, representation, and description. Under the name column are the following: alpha particle, beta particle, positron, proton, neutron, and gamma ray. Under the symbol S column are the following: superscript 4 stacked over a subscript 2 He, or lowercase alpha. Superscript 0 stacked over a subscript 1e, or lowercase beta. Superscript 0 stacked over a positive subscript 1e, or lowercase beta, superscript positive sign. Superscript 1 stacked over a subscript 1h, or lowercase, row superscript 1 stacked over a subscript 1h. Superscript 1 stacked over a subscript 0n, or lowercase, eta superscript 1 stacked over a subscript 0n, and a lowercase gamma. Under the representation column are the following: 2 white spheres attached to 2 blue spheres of about the same size with positive signs in them, a small red sphere with a negative sign in it, a small red sphere with a positive sign in it, a blue sphere with a positive sign in it, a white sphere, and a purple squiggle ling with an arrow pointing right to a lowercase gamma. Under the description column are the following: high-energy helium nuclei consisting of 2 protons and 2 neutrons. High-energy electrons, particles with the same mass as an electron but with 1 unit of positive charge. Nuclei of hydrogen atoms, particles with a mass approximately equal to that of a proton but with no charge. And very high-energy electromagnetic radiation. Figure 21. Although many species are encountered in nuclear reactions, this table summarizes the names, symbols, representations, and descriptions of the most common of these. Note that positrons are exactly like electrons, except they have the opposite charge. They are the most common example of antimatter, particles with the same mass but the opposite state of another property, for example, charge, than ordinary matter. When antimatter encounters ordinary matter, both are annihilated and their mass is converted into energy in the form of gamma rays gamma, and other much smaller subnuclear particles, which are beyond the scope of this chapter. According to the mass-energy equivalence equation E equals mc2, seen in the preceding section. For example, when a positron and an electron collide, both are annihilated and 2 gamma-ray photons are created. 0 minus 1e plus 0 plus 1e gamma plus gamma. As seen in the chapter discussing light and electromagnetic radiation, gamma rays compose short wavelength, high-energy electromagnetic radiation, and are much more energetic than better-known X-rays that can behave as particles in the wave-particle duality sense. Gamma rays are a type of high-energy electromagnetic radiation produced when a nucleus undergoes a transition from a higher to a lower energy state, similar to how a photon is produced by an electronic transition from a higher to a lower energy level. Due to the much larger energy differences between nuclear energy shells, gamma rays emanating from a nucleus have energies that are typically millions of times larger than electromagnetic radiation emanating from electronic transitions. Balancing nuclear reactions. A balanced chemical reaction equation reflects the fact that during a chemical reaction, bonds break and form, and atoms are rearranged, but the total numbers of atoms of each element are conserved and do not change. A balanced nuclear reaction equation indicates that there is a rearrangement during a nuclear reaction, but of nucleons, subatomic particles within the atom's nuclei, rather than atoms. Nuclear reactions also follow conservation laws, and they are balanced in 2 ways. The sum of the mass numbers of the reactants equals the sum of the mass numbers of the products. The sum of the charges of the reactants equals the sum of the charges of the products. If the atomic number and the mass number of all but one of the particles in a nuclear reaction are known, we can identify the particle by balancing the reaction. For instance, we could determine that 178O is a product of the nuclear reaction of 147 N and 42 He. If we knew that a proton, 11H, was one of the two products, example 21, 4 shows how we can identify a nuclide by balancing the nuclear reaction. Example 21, 4. Balancing equations for nuclear reactions. The reaction of an alpha particle with magnesium-25, 2512 Mg, produces a proton and a nuclide of another element. Identify the new nuclide produced. Solution. The nuclear reaction can be written as 2512 Mg plus 42 He 11H plus asks, where A is the mass number and Z is the atomic number of the new nuclide, X. Because the sum of the mass numbers of the reactants must equal the sum of the mass numbers of the products. 25 plus 4 equals A plus 1, or A equals 28. Similarly, the charges must balance, so 12 plus 2 equals Z plus 1, and Z equals 13. Check the periodic table. The element with nuclear charge equals plus 13 is aluminum. Thus, the product is 2813 Al. Check your learning. The nuclide 12553 I combines with an electron and produces a new nucleus and no other massive particles. What is the equation for this reaction? Answer: 12,553 plus 0 minus 1e 12,552t. Following are the equations of several nuclear reactions that have important roles in the history of nuclear chemistry. The first naturally occurring unstable element that was isolated, polonium, was discovered by the Polish scientist Marie Curie and her husband Pierre in 1898. It decays, emitting alpha particles, 21,284 Po, 20,882 Pb plus 42 He. The first nuclide to be prepared by artificial means was an isotope of oxygen, 17O. It was made by Ernest Rutherford in 1919 by bombarding nitrogen atoms with alpha particles, 147 N plus 42 He 178 O plus 11H. James Chadwick discovered the neutron in 1932 as a previously unknown neutral particle produced along with 12C by the nuclear reaction between 9B and 4 He. 94B plus 42 He 126C plus 10N. The first element to be prepared that does not occur naturally on the Earth, technetium, was created by bombardment of molybdenum by deuterons, heavy hydrogen, 21H, by Emilio Segur and Carlo Perrier in 1937. 21H plus 9,742, Mo 210N plus 9,743 Tc. The first controlled nuclear chain reaction was carried out in a reactor at the University of Chicago in 1942. One of the many reactions involved was 23,592 U plus 10 N 8,735 Br plus 14,657 La plus 310 N. Learning objectives. By the end of this section, you will be able to recognize common modes of radioactive decay, identify common particles and energies involved in nuclear decay reactions, write and balance nuclear decay equations, calculate kinetic parameters for decay processes, including half-life, describe common radiometric dating techniques. Following the somewhat serendipitous discovery of radioactivity by Becquerel, many prominent scientists began to investigate this new, intriguing phenomenon. Among them were Marie Curie, the first woman to win a Nobel Prize, and the only person to win 2 Nobel Prizes in different sciences, chemistry and physics, who was the first to coin the term radioactivity, and Ernest Rutherford of gold foil experiment fame, who investigated and named 3 of the most common types of radiation. During the beginning of the 20th century, many radioactive substances were discovered. The properties of radiation were investigated and quantified, and a solid understanding of radiation and nuclear decay was developed. The spontaneous change of an unstable nuclide into another is radioactive decay. The unstable nuclide is called the parent nuclide. The nuclide that results from the decay is known as the daughter nuclide. The daughter nuclide may be stable, or it may decay itself. The radiation produced during radioactive decay is such that the daughter nuclide lies closer to the band of stability than the parent nuclide. So the location of a nuclide relative to the band of stability can serve as a guide to the kind of decay it will undergo. Figure 21. 5. A diagram shows two spheres composed of many smaller white and green spheres connected by a right-facing arrow with another, down-facing arrow coming off of it. The left sphere, labeled parent nucleus uranium-238, has two white and two green spheres that are near one another and are outlined in red. These two green and two white spheres are shown near the tip of the down-facing arrow and labeled alpha particle. The right sphere, labeled daughter nucleus radon-234, looks the same as the left, but has a space for four smaller spheres outlined with a red dotted line. Figure 21. 5. A nucleus of uranium-238, the parent nuclide, undergoes alpha decay to form thorium-234, the daughter nuclide. The alpha particle removes two protons green and two neutrons gray from the uranium-238 nucleus. Link to learning. Although the radioactive decay of a nucleus is too small to see with the naked eye, we can indirectly view radioactive decay in an environment called a cloud chamber. Click here to learn about cloud chambers and to view an interesting cloud chamber demonstration from the Jefferson Lab. Types of radioactive decay. Ernest Rutherford's experiments involving the interaction of radiation with a magnetic or electric field, Figure 21. 6. Helped him determine that one type of radiation consisted of positively charged and relatively massive alpha particles. A second type was made up of negatively charged and much less massive beta particles. And a third was uncharged electromagnetic waves, gamma rays. We now know that alpha particles are high-energy helium nuclei, beta particles are high-energy electrons, and gamma radiation compose high-energy electromagnetic radiation. We classify different types of radioactive decay by the radiation produced. A diagram is shown. A gray box on the left side of the diagram labeled lead block has a chamber hollowed out in the center in which a sample labeled radioactive substance is placed. A blue beam is coming from the sample out of the block and passing through two horizontally placed plates that are labeled electrically charged plates. The top plate is labeled with a positive sign, while the bottom plate is labeled with a negative sign. The beam is shown to break into three beams as it passes in between the plates. In order from top to bottom, they are red, labeled beta rays, purple labeled gamma rays, and green labeled alpha rays. The beams are shown to hit a vertical plate labeled photographic plate on the far right side of the diagram. Figure 21. 6 alpha particles, which are attracted to the negative plate and deflected by a relatively small amount, must be positively charged and relatively massive. Beta particles, which are attracted to the positive plate and deflected a relatively large amount, must be negatively charged and relatively light. Gamma rays, which are unaffected by the electric field, must be uncharged. Alpha-alpha decay is the emission of an alpha particle from the nucleus. For example, polonium-210 undergoes alpha decay. 21,084 Po42, He plus 20,682, P-bor 21,084 Po42 alpha plus 20,682 Pb. Alpha decay occurs primarily in heavy nuclei A200, Z83. Because the loss of an alpha particle gives a daughter nuclide with a mass number 4 units smaller and an atomic number 2 units smaller than those of the parent nuclide, the daughter nuclide has a larger N-P ratio than the parent nuclide. If the parent nuclide undergoing alpha decay lies below the band of stability, refer to Figure 21. 2. The daughter nuclide will lie closer to the band. Beta-beta decay is the emission of an electron from a nucleus. Iodine-131 is an example of a nuclide that undergoes beta decay. 13,153, I0 minus 1 E plus 13,154 Zior 13,153, I0 minus 1 beta plus 13,154 Z. Beta decay, which can be thought of as the conversion of a neutron into a proton and a beta particle, is observed in nuclides with a large N. P ratio. The beta particle electron emitted is from the atomic nucleus and is not one of the electrons surrounding the nucleus. Such nuclei lie above the band of stability. Emission of an electron does not change the mass number of the nuclide, but does increase the number of its protons and decrease the number of its neutrons. Consequently, the N-P ratio is decreased, and the daughter nuclide lies closer to the band of stability than did the parent nuclide. Gamma emission. Gamma emission is observed when a nuclide is formed in an excited state and then decays to its ground state with the emission of a gamma ray, a quantum of high-energy electromagnetic radiation. The presence of a nucleus in an excited state is often indicated by an asterisk asterisk. Cobalt-60 emits gamma radiation and is used in many applications including cancer treatment. 6027 Co*00 gamma plus 6027 Co. There is no change in mass number or atomic number during the emission of a gamma ray, unless the gamma emission accompanies one of the other modes of decay. Positron emission, decay, is the emission of a positron from the nucleus. Oxygen-15 is an example of a nuclide that undergoes positron emission. 158O0 plus 1E plus 157, nor 158O0 plus 1 beta plus 157N. Positron emission is observed for nuclides in which the N-P ratio is low. These nuclides lie below the band of stability. Positron decay is the conversion of a proton into a neutron with the emission of a positron. The N-P ratio increases, and the daughter nuclide lies closer to the band of stability than did the parent nuclide. Electron capture occurs when one of the inner electrons in an atom is captured by the atom's nucleus. For example, potassium-40 undergoes electron capture. 4019 K plus 0 minus 1 E 4018 R. Electron capture occurs when an inner shell electron combines with a proton and is converted into a neutron. The loss of an inner shell electron leaves a vacancy that will be filled by one of the outer electrons. As the outer electron drops into the vacancy, it will emit energy. In most cases, the energy emitted will be in the form of an X-ray. Like positron emission, electron capture occurs for proton-rich nuclei that lie below the band of stability. Electron capture has the same effect on the nucleus as does positron emission. The atomic number is decreased by 1 and the mass number does not change. This increases the N-P ratio, and the daughter nuclide lies closer to the band of stability than did the parent nuclide. Whether electron capture or positron emission occurs is difficult to predict. The choice is primarily due to kinetic factors, with the one requiring the smaller activation energy being the one more likely to occur. Figure 21.7 summarizes these types of decay, along with their equations and changes in atomic and mass numbers. This table has 4 columns and 6 rows. The first row is a header row and it labels each column. Type, nuclear equation, representation, and change in mass/atomic numbers. Under the type column are the following: alpha decay, beta decay, gamma decay, positron emission, and electron capture. Under the nuclear equation column are several equations. Each begins with superscript A stacked over subscript ZX. There is a large gap of space, and then the following equations. Superscript 4 stacked over subscript 2 he plus superscript a minus 4 stacked over subscript z minus 2y. Superscript 0 stacked over subscript negative 1e plus superscript a stacked over subscript z plus 1y. Superscript 0 stacked over subscript 0 lowercase gamma plus superscript a stacked over subscript zy. Superscript 0 stacked over subscript positive 1e plus superscript a stacked over subscript y minus 1y. And superscript 0 stacked over subscript negative 1e plus superscript a stacked over subscript y minus 1y. Under the representation column are the 5 diagrams. The first shows a cluster of green and white spheres. A section of the cluster containing 2 white and 2 green spheres is outlined. There is a right-facing arrow pointing to a similar cluster as previously described, but the outlined section is missing. From the arrow, another arrow branches off and points downward. The small cluster to 2 white spheres and 2 green spheres appear at the end of the arrow. The next diagram shows the same cluster of white and green spheres. 1 white sphere is outlined. There is a right-facing arrow to a similar cluster, but the white sphere is missing. Another arrow branches off the main arrow, and a red sphere with a negative sign appears at the end. The next diagram shows the same cluster of white and green spheres. The whole sphere is outlined and labeled excited nuclear state. There is a right-facing arrow that points to the same cluster. No spheres are missing. Off the main arrow is another arrow which points to a purple squiggle arrow, which in turn points to a lowercase gamma. The next diagram shows the same cluster of white and green spheres. 1 green sphere is outlined. There is a right-facing arrow to a similar cluster, but the green sphere is missing. Another arrow branches off the main arrow, and a red sphere with a positive sign appears at the end. The next diagram shows the same cluster of white and green spheres. 1 green sphere is outlined. There is a right-facing arrow to a similar cluster, but the green sphere is missing. 2 other arrows branch off the main arrow. The first shows a gold sphere with a negative sign joining with the right-facing arrow. The second points to a blue squiggle arrow labeled X-ray. Under the change in mass/atomic numbers column are the following: A. Decrease by 4 Z, decrease by 2. A. Unchanged Z, increase by 1. A. Unchanged Z, unchanged. A. Unchanged Z, unchanged. A. Unchanged Z, decrease by 1, and A. Unchanged Z. Decrease by 1. Figure 21. 7. This table summarizes the type, nuclear equation, representation, and any changes in the mass or atomic numbers for various types of decay. Chemistry in everyday life. PET scan, positron emission tomography, PET. Scans use radiation to diagnose and track health conditions and monitor medical treatments by revealing how parts of a patient's body function. Figure 21. 8. To perform a PET scan, a positron-emitting radioisotope is produced in a cyclotron and then attached to a substance that is used by the part of the body being investigated. This tagged compound or radiotracer is then put into the patient, injected via IV or breathed in as a gas, and how it is used by the tissue reveals how that organ or other area of the body functions. 3 pictures are shown and labeled A, B, and C. Picture A shows a machine with a round opening connected to an examination table. Picture B is a medical scan of the top of a person's head and shows large patches of yellow and red and smaller patches of blue, green, and purple highlighting. Picture C also shows a medical scan of the top of a person's head, but this image is mostly colored in blue and purple with very small patches of red and yellow. Figure 21. 8. A PET scanner A uses radiation to provide an image of how part of a patient's body functions. The scans it produces can be used to image a healthy brain B, or can be used for diagnosing medical conditions such as Alzheimer's disease C. Credit A. Modification of work by Jens Mouse. For example, F-18 is produced by proton bombardment of 18O, 188 O plus 11 P 189 F plus 10 N, and incorporated into a glucose analog called fludeoxyglucose, FDG. How FDG is used by the body provides critical diagnostic information. For example, since cancers use glucose differently than normal tissues, FDG can reveal cancers. The 18F emits positrons that interact with nearby electrons, producing a burst of gamma radiation. This energy is detected by the scanner and converted into a detailed, three-dimensional color image that shows how that part of the patient's body functions. Different levels of gamma radiation produce different amounts of brightness and colors in the image, which can then be interpreted by a radiologist to reveal what is going on. PET scans can detect heart damage and heart disease, help diagnose Alzheimer's disease, indicate the part of a brain that is affected by epilepsy, reveal cancer, show what stage it is, and how much it has spread, and whether treatments are effective. Unlike magnetic resonance imaging and X-rays, which only show how something looks, the big advantage of PET scans is that they show how something functions. PET scans are now usually performed in conjunction with a computed tomography scan. Radioactive decay series. The naturally occurring radioactive isotopes of the heaviest elements fall into chains of successive disintegrations, or decays, and all the species in one chain constitute a radioactive family, or radioactive decay series. 3 of these series include most of the naturally radioactive elements of the periodic table. They are the uranium series, the actinide series, and the thorium series. The neptunium series is a 4th series, which is no longer significant on the Earth because of the short half-lives of the species involved. Each series is characterized by a parent first member that has a long half-life and a series of daughter nuclides that ultimately lead to a stable end product. That is, a nuclide on the band of stability, figure 21. 9. In all 3 series, the end product is a stable isotope of lead. The neptunium series, previously thought to terminate with bismuth-209, terminates with thallium-205. A graph is shown where the x-axis is labeled number of neutrons, open parenthesis, n, close parenthesis, and has values of 122 to 148 in increments of 2. The y-axis is labeled atomic number and has values of 80 to 92 in increments of 1. 2 types of arrows are used in this graph to connect the points. Green arrows are labeled as alpha decay, while red arrows are labeled beta decay. Beginning at the point 92, 146, that is labeled superscript 238 U, a green arrow connects this point to the second point 90, 144, which is labeled superscript 234 TA. A red arrow connects this to the third point 91, 143, which is labeled superscript 234 PA, which is connected to the fourth point 92, 142 by a red arrow and which is labeled superscript 234 U. A green arrow leads to the next point, 90, 140, which is labeled superscript 230 TH, and is connected by a green arrow to the sixth point, 88, 138, which is labeled superscript 226 R, that is in turn connected by a green arrow to the seventh point 86, 136, which is labeled superscript 222 Ra. The eighth point at 84, 134 is labeled superscript 218 PO and has green arrows leading to it and away from it to the ninth point 82, 132, which is labeled superscript 214 PB, which is connected by a red arrow to the 10th point, 83, 131, which is labeled superscript 214 BI. A red arrow leads to the 11th point, 84, 130, which is labeled superscript 214 PO, and a green arrow leads to the 12th point, 82, 128, which is labeled superscript 210 pb. A red arrow leads to the 13th point 83, 127, which is labeled superscript 210, bi, and a red arrow leads to the 14th point 84, 126, which is labeled superscript 210, po. The final point is labeled 82, 124, and superscript 206, pb. Figure 21. 9-uranium-238 undergoes a radioactive decay series consisting of 14 separate steps before producing stable lead-206. This series consists of 8 alpha decays and 6 beta decays. Radioactive half-lives. Radioactive decay follows first-order kinetics. Since first-order reactions have already been covered in detail in the kinetics chapter, we will now apply those concepts to nuclear decay reactions. Each radioactive nuclide has a characteristic constant half-life, T12, the time required for half of the atoms in a sample to decay. An isotope's half-life allows us to determine how long a sample of a useful isotope will be available, and how long a sample of an undesirable or dangerous isotope must be stored before it decays to a low enough radiation level that is no longer a problem. For example, cobalt-60, an isotope that emits gamma rays used to treat cancer, has a half-life of 527 years, figure 21. 10. In a given cobalt-60 source, since half of the 6027 nuclei decay every 527 years, both the amount of material and the intensity of the radiation emitted is cut in half every 527 years. Note that for a given substance, the intensity of radiation that it produces is directly proportional to the rate of decay of the substance and the amount of the substance. This is as expected for a process following first-order kinetics. Thus, a cobalt-60 source that is used for cancer treatment must be replaced regularly to continue to be effective. A graph titled CO-60 decay is shown where the x-axis is labeled CO-60 remaining, open parenthesis, %, close parenthesis, and has values of 0 to 100 in increments of 25. The y-axis is labeled number of half-lives and has values of 0 to 5 in increments of 1. The first point, at 0, 100, has a circle filled with tiny dots drawn near it labeled 10G. The second point, at 150, has a smaller circle filled with tiny dots drawn near it labeled 5G. The third point, at 225, has a small circle filled with tiny dots drawn near it labeled 2. 5G. The fourth point, at 312.5, has a very small circle filled with tiny dots drawn near it labeled 125G. The last point, at 4.635, has a tiny circle filled with tiny dots drawn near it labeled 625G. Figure 21. 10 for cobalt-60, which has a half-life of 5.27 years. 50% remains after 5.27 years, 1 half-life. 25% remains after 10. 54 years, 2 half-lives, 12. 5% remains after 15. 81 years, 3 half-lives, and so on. Since nuclear decay follows first-order kinetics, we can adapt the mathematical relationships used for first-order chemical reactions. We generally substitute the number of nuclei, n, for the concentration. If the rate is stated in nuclear decays per second, we refer to it as the activity of the radioactive sample. The rate for radioactive decay is decay rate equals lambda n, with lambda equals the decay constant for the particular radioisotope. The decay constant lambda, which is the same as a rate constant discussed in the kinetics chapter. It is possible to express the decay constant in terms of the half-life, T12. Letter 1D706 equals ln2, letter 1D461 1/2 equals 0. 693 letter 1D461 1/2 OR letter 1D461 1/2 equals ln2 letter 1D706 equals 0. 693 letter 1D706 The first-order equations relating amount, n, and time are letter 1d441, letter 1d461 equals letter 1d4410, letter 1d452, minus letter 1d706, letter 1d461. OR letter 1d461 equals minus 1, letter 1d706 ln. Letter 1d441, letter 1d461, letter 1d4410, where N0 is the initial number of nuclei, or moles of the isotope, and Nt is the number of nuclei moles remaining at time t. Example 21. 5 applies these calculations to find the rates of radioactive decay for specific nuclides. Example 21. 5. Rates of radioactive decay. 6027 Co. Decays with a half-life of 27 years to produce 6028 Ni. A. What is the decay constant for the radioactive disintegration of cobalt-60? B. Calculate the fraction of a sample of the 6027 Co. isotope that will remain after 15 years. C. How long does it take for a sample of 6027 Co. to disintegrate to the extent that only 20% of the original amount remains? Solution. A. The value of the rate constant is given by letter 1d706 equals ln2, letter 1d461 1/2 equals 0. 6935. 27y equals 0. 132y minus 1. B. The fraction of 6027 Co. that is left after time t is given by letter 1d441, letter 1d461, letter 1d4410. Rearranging the first-order relationship Nt equals N0, E. Lambda to solve for this ratio yields letter 1d441, letter 1d461, letter 1d4410 equals letter 1d452 minus letter 1d706, letter 1d461 equals letter 1d452 minus 0. 132/y, 15 times y equals 0. 138. The fraction of 6027 Co. that will remain after 15 years is 0. 138. Or put another way, 13.8% of the 6027 Co. originally present will remain after 15 years. C. 20% of the original amount of 6027 Co. is equal to 0. 200 times N0. Substituting this into the equation for time for first-order kinetics, we have letter 1d461 equals minus 1 letter 1d706 ln, letter 1d441, letter 1d461, letter 1d4410 equals minus 10. 132 y minus 1 ln 0. 0200 times letter 1d4410, letter 1d4410 equals 29. 6y. Check your learning. Radon 222, 22,286 Rn. Has a half-life of 3,823 days. How long will it take a sample of radon 222 with a mass of 0.750 g to decay into other elements, leaving only 0.100 g of radon 222? Answer: 11 days. Because each nuclide has a specific number of nucleons, a particular balance of repulsion and attraction, and its own degree of stability, the half-lives of radioactive nuclides vary widely. For example, the half-life of 20,983 Bi is 19 times 1019 years. 23,994 Ra is 24,000 years. 22,286 Rn is 382 days. And element 111 Rg for rentgenium is 15 times 10 seconds. The half-lives of a number of radioactive isotopes important to medicine are shown in Table 21. 2. And others are listed in Appendix M. Half-lives of radioactive isotopes important to medicine. Type 1 decay mode half-life uses. F18 decay 110 minutes. PET scans. Co60 beta decay, gamma decay 5, 27 years cancer treatment. TC99M gamma decay 8, 1 hour scans of brain, lung, heart, bone. 130, 1 beta decay 8. 2 days thyroid scans and treatment. TL 201, electron capture 73 hours heart and arteries scans. Cardiac stress tests. Table 21. 2. Radiometric dating. Several radioisotopes have half-lives and other properties that make them useful for purposes of dating the origin of objects such as archaeological artifacts, formerly living organisms, or geological formations. This process is radiometric dating and has been responsible for many breakthrough scientific discoveries about the geological history of the Earth, the evolution of life, and the history of human civilization. We will explore some of the most common types of radioactive dating and how the particular isotopes work for each type. Radioactive dating using carbon-14. The radioactivity of carbon-14 provides a method for dating objects that were a part of a living organism. This method of radiometric dating, which is also called radiocarbon dating or carbon-14 dating, is accurate for dating carbon-containing substances that are up to about 30,000 years old and can provide reasonably accurate dates up to a maximum of about 50,000 years old. Naturally occurring carbon consists of 3 isotopes, 126C, which constitutes about 99% of the carbon on Earth, 136C, about 1% of the total, and trace amounts of 146C. Carbon-14 forms in the upper atmosphere by the reaction of nitrogen atoms with neutrons from cosmic rays in space. 140, 7N plus 10N 146C plus 11H. All isotopes of carbon react with oxygen to produce CO2 molecules. The ratio of 146 CO2 to CO depends on the ratio of 146 CO to 126 CO. In the atmosphere, the natural abundance of 146 CO in the atmosphere is approximately 1 part per trillion. Until recently, this has generally been constant over time, as seen as gas samples found trapped in ice. The incorporation of 146C, 146 CO2, and CO into plants is a regular part of the photosynthesis process, which means that the 146C, 126C ratio found in a living plant is the same as the 146C, 126C ratio in the atmosphere. But when the plant dies, it no longer traps carbon through photosynthesis, because 126C is a stable isotope and does not undergo radioactive decay. Its concentration in the plant does not change. However, carbon-14 decays by beta emission with a half-life of 5730 years. 146C, 147N plus 0 minus 1E. Thus, the 146C, 126C ratio gradually decreases after the plant dies. The decrease in the ratio with time provides a measure of the time that has elapsed since the death of the plant or other organism that ate the plant. Figure 21. 11 visually depicts this process. A diagram shows a cow standing on the ground next to a tree. In the upper left of the diagram, where the sky is represented, a single white sphere is shown and is connected by a downward-facing arrow to a larger sphere composed of green and white spheres that is labeled superscript 14, subscript 7, N. This structure is connected to 3 other structures by a right-facing arrow. Each of the 3 it points to are composed of green and white spheres, and all have arrows pointing from them to the ground. The first of these is labeled trace, superscript 14, subscript 6C. The second is labeled 1%, superscript 13, subscript 6C. And the last is labeled 99%, superscript 12, subscript 6C. 2 downward-facing arrows that merge into one arrow lead from the cow and tree to the ground and are labeled organism dies, and superscript 14, subscript 6, C, decay begins. A right-facing arrow labeled on top as decay, and on bottom as time, leads from this to a label of superscript 14, subscript 6, C superscript 12 subscript 6 C ratio decreased. Near the top of the tree is a downward-facing arrow with the label superscript 14 subscript 6 C superscript 12 subscript 6 C ratio is constant in living organisms. That leads to the last of the lower statements. Figure 21. 11 along with stable carbon-12, radioactive carbon-14 is taken in by plants and animals and remains at a constant level within them while they are alive. After death, the C14 decays and the C12 ratio in the remains decreases. Comparing this ratio to the C12 ratio in living organisms allows us to determine how long ago the organism lived and died. For example, with the half-life of 146C being 5730 years, if the 126C ratio in a wooden object found in an archaeological dig is half what it is in a living tree, this indicates that the wooden object is 5730 years old. Highly accurate determinations of 146C, 126C ratios can be obtained from very small samples, as little as a milligram, by the use of a mass spectrometer. Link to learning. Visit this website to perform simulations of radiometric dating. Example 21. 6. Radiocarbon dating. A tiny piece of paper, produced from formerly living plant matter, taken from the Dead Sea Scrolls, has an activity of 10.8 disintegrations per minute per gram of carbon. If the initial C14 activity was 13.6 disintegrations min-G of C, estimate the age of the Dead Sea Scrolls. Solution. The rate of decay, number of disintegrations minute gram of carbon, is proportional to the amount of radioactive C14 left in the paper, so we can substitute the rates for the amounts, N, in the relationship. Letter 1D461 equals -1, letter 1D706 letter 1D441, letter 1D461, letter 1D4410. Letter 1D461 equals -1, letter 1D706 R a T, E letter 1D461 rate 0, where the subscript 0 represents the time when the plants were cut to make the paper, and the subscript T represents the current time. The decay constant can be determined from the half-life of C14, 5730 years. Letter 1D706 equals ln2, letter 1D461 1/2 equals 0. 6,930,5,730 y equals 1. 21 times 10⁻4 y-1. Substituting and solving, we have rate 21 times 10⁻4 y-1 ln 10. 8 dis min gc 13. 6 dis min gc equals 1910 y. Therefore, the Dead Sea Scrolls are approximately 1900 years old. Figure 21. 12. A photograph of 6 pages of ragged-edged paper covered in writing are shown. Figure 21. 12 carbon-14 dating has shown that these pages from the Dead Sea Scrolls were written or copied on paper made from plants that died between 100 BC and AD 50. Check your learning. More accurate dates of the reigns of ancient Egyptian pharaohs have been determined recently, using plants that were preserved in their tombs. Samples of seeds and plant matter from King Tutankhamun's tomb have a C14 decay rate of 9.7 disintegrations min-G of C. How long ago did King Tut's reign come to an end? Answer. About 3,350 years ago, or approximately 1340 BC. There have been some significant, well-documented changes to the 146C, 126C ratio. The accuracy of a straightforward application of this technique depends on the 146C, 126C ratio in a living plant being the same now as it was in an earlier era, but this is not always valid, due to the increasing accumulation of CO2 molecules, largely CO, in the atmosphere caused by combustion of fossil fuels, in which essentially all of the 146C has decayed. the ratio of 146C. 126C. In the atmosphere may be changing. This man-made increase in Co. in the atmosphere causes the 146C. 126C. ratio to decrease, and this in turn affects the ratio in currently living organisms on the Earth. Fortunately, however, we can use other data, such as tree dating via examination of annual growth rings, to calculate correction factors. With these correction factors, accurate dates can be determined. In general, radioactive dating only works for about 10 half-lives. Therefore, the limit for carbon-14 dating is about 57,000 years. Radioactive dating, using nuclides other than carbon-14. Radioactive dating can also use other radioactive nuclides with longer half-lives to date older events. For example, uranium-238, which decays in a series of steps into lead-206, can be used for establishing the age of rocks and the approximate age of the oldest rocks on Earth. Since U-238 has a half-life of 4-5 billion years, it takes that amount of time for half of the original U-238 to decay into Pb-206. In a sample of rock that does not contain appreciable amounts of Pb-208, the most abundant isotope of lead, we can assume that lead was not present when the rock was formed. Therefore, by measuring and analyzing the ratio of U-238, Pb-206, we can determine the age of the rock. This assumes that all of the lead-206 present came from the decay of uranium-238. If there is additional lead-206 present, which is indicated by the presence of other lead isotopes in the sample, it is necessary to make an adjustment. Potassium-argon dating uses a similar method. K40 decays by positron emission and electron capture to form R40 with a half-life of 125 billion years. If a rock sample is crushed and the amount of R40 gas that escapes is measured, determination of the R40, K40 ratio yields the age of the rock. Other methods, such as rubidium-strontium dating, RB87 decays into SR87 with a half-life of 8 billion years, operate on the same principle. To estimate the lower limit for the Earth's age, scientists determine the age of various rocks and minerals, making the assumption that the Earth is older than the oldest rocks and minerals in its crust. As of 2014, the oldest known rocks on Earth are the Jack Hills zircons from Australia, found by uranium lead dating to be almost 4 billion years old. Example 21. 7. Radioactive dating of rocks. An igneous rock contains 58 times 10⁵ G of U-238 and 251 times 10⁵ G of Pb-206 and much smaller amounts of Pb-208. Determine the approximate time at which the rock formed. Solution. The sample of rock contains very little Pb-208, the most common isotope of lead, so we can safely assume that all the Pb-206 in the rock was produced by the radioactive decay of U-238. When the rock formed, it contained all of the U-238 currently in it, plus some U-238 that has since undergone radioactive decay. The amount of U-238 currently in the rock is 58 times 10⁻⁵ Gu times 1 mol U-238 Gu equals 4.03 times 10⁻⁷ mol U. Because when 1 mole of U-238 decays, it produces 1 mole of Pb-206. The amount of U-238 that has undergone radioactive decay since the rock was formed is 51 times 10⁻⁵ G Pb times 1 mol Pb-206 G Pb times 1 mol U 1 mol Pb equals 1.22 times 10⁻⁷ mol U. The total amount of U-238 originally present in the rock is therefore 4.03 times 10⁻⁷ mol plus 1.22 times 10⁻⁷ mol equals 5.25 times 10⁻⁷ mol U. The amount of time that has passed since the formation of the rock is given by letter 1D461 equals minus 1, letter 1D706LN, letter 1D441, letter 1D461, letter 1D4410, with N0 representing the original amount of U238, and NT representing the present amount of U238. U238 decays into Pb206 with a half-life of 4-5 times 109Y, so the decay constant lambda is letter 1D706 equals Ln2, letter 1D461, 1/2 equals 0. 6934. 5 times 109Y equals 1. 54 times 10 minus 10Y minus 1. Substituting and solving, we have letter 1D461 equals minus 11. 54 times 10 minus 10Y minus 1 Ln4. 0 3 times 10 minus 7 mol U5. 25 times 10 minus 7 mol U equals 1. 7 times 109Y. Therefore, the rock is approximately 17 billion years old. Check your learning. A sample of rock contains 614 times 10·4 of Rb87 and 351 times 10·5 of Sr87. Calculate the age of the rock. The half-life of the beta decay of Rb87 is 47 times 10·10Y. Answer 37 times 109Y. Learning objectives. By the end of this section, you will be able to describe the synthesis of transuranium nuclides, explain nuclear fission and fusion processes, relate the concepts of critical mass and nuclear chain reactions, summarize basic requirements for nuclear fission and fusion reactors. After the discovery of radioactivity, the field of nuclear chemistry was created and developed rapidly during the early 20th century. A slew of new discoveries in the 1930s and 1940s, along with World War II, combined to usher in the nuclear age in the mid-20th century. Scientists learned how to create new substances, and certain isotopes of certain elements were found to possess the capacity to produce unprecedented amounts of energy, with the potential to cause tremendous damage during war, as well as produce enormous amounts of power for society's needs during peace. Synthesis of nuclides. Nuclear transmutation is the conversion of one nuclide into another. It can occur by the radioactive decay of a nucleus or the reaction of a nucleus with another particle. The first man-made nucleus was produced in Ernest Rutherford's laboratory in 1919 by a transmutation reaction, the bombardment of one type of nuclei with other nuclei or with neutrons. Rutherford bombarded nitrogen atoms with high-speed alpha particles from a natural radioactive isotope of radium and observed protons resulting from the reaction. NHOA, the 178O and 11H nuclei that are produced are stable, so no further nuclear changes occur. To reach the kinetic energies necessary to produce transmutation reactions, devices called particle accelerators are used. These devices use magnetic and electric fields to increase the speeds of nuclear particles. In all accelerators, the particles move in a vacuum to avoid collisions with gas molecules. When neutrons are required for transmutation reactions, they are usually obtained from radioactive decay reactions or from various nuclear reactions occurring in nuclear reactors. The chemistry and everyday life feature that follows discusses a famous particle accelerator that made worldwide news. Chemistry in everyday life. CERN Particle Accelerator. Located near Geneva, the CERN, Conseil Européen pour la Recherche Nucléaire, or European Council for Nuclear Research, laboratory is the world's premier center for the investigations of the fundamental particles that make up matter. It contains the 27-kilometer, 17-mile, long circular Large Hadron Collider, LHC, the largest particle accelerator in the world, figure 2113. In the LHC, particles are boosted to high energies and are then made to collide with each other or with stationary targets at nearly the speed of light. Superconducting electromagnets are used to produce a strong magnetic field that guides the particles around the ring. Specialized, purpose-built detectors observe and record the results of these collisions, which are then analyzed by CERN scientists using powerful computers. Two photos are shown and labeled A and B. Photo A shows an aerial view of the Large Hadron Collider. Photo B shows a tunnel of concrete with rails on the ground and tubes and wires running along the wall. Two people walk along the tunnel. Figure 21. 13. A small section of the LHC is shown with workers traveling along it. Credit: Christophe Dallaire. In 2012, CERN announced that experiments at the LHC showed the first observations of the Higgs boson, an elementary particle that helps explain the origin of mass in fundamental particles. This long-anticipated discovery made worldwide news and resulted in the awarding of the 2013 Nobel Prize in Physics to Francois Englert and Peter Higgs, who had predicted the existence of this particle almost 50 years previously. Link to learning. Famous physicist Brian Cox talks about his work on the Large Hadron Collider at CERN, providing an entertaining and engaging tour of this massive project and the physics behind it. View a short video from CERN describing the basics of how its particle accelerators work. Prior to 1940, the heaviest known element was uranium, whose atomic number is 92. Now, many artificial elements have been synthesized and isolated, including several on such a large scale that they have had a profound effect on society. One of these, element 93, neptunium, Np, was first made in 1940 by Macmillan and Abelson by bombarding uranium-238 with neutrons. The reaction creates unstable uranium-239 with a half-life of 23.5 minutes, which then decays into neptunium-239. Neptunium is also radioactive with a half-life of 2.36 days, and it decays into plutonium-239. The nuclear reactions are 23,892, U plus 10 N 23,992, U 23,992, U 23,993, Np, plus 0 minus 1 half-life equals 23. 5 min 23,993, Np 23,994, Pu plus 0 minus 1 half-life equals 2.36 days. Plutonium is now mostly formed in nuclear reactors as a byproduct during the fission of U-235. Additional neutrons are released during this fission process. See the next section. Some of which combine with U-238 nuclei to form uranium-239. This undergoes beta decay to form neptunium-239, which in turn undergoes beta decay to form plutonium-239, as illustrated in the preceding three equations. These processes are summarized in the equation 23,892, U plus 10 N 23,992, U minus right minus beta minus 23,993, Np minus right minus beta minus 23,994 Pu. Heavier isotopes of plutonium, Pu-240, Pu-241, and Pu-242, are also produced when lighter plutonium nuclei capture neutrons. Some of this highly radioactive plutonium is used to produce military weapons, and the rest presents a serious storage problem because they have half-lives from thousands to hundreds of thousands of years. Although they have not been prepared in the same quantity as plutonium, many other synthetic nuclei have been produced. Nuclear medicine has developed from the ability to convert atoms of one type into other types of atoms. Radioactive isotopes of several dozen elements are currently used for medical applications. The radiation produced by their decay is used to image or treat various organs or portions of the body, among other uses. The elements beyond element 92, uranium, are called transuranium elements. As of this writing, 22 transuranium elements have been produced and officially recognized by IUPAC. Several other elements have formation claims that are waiting for approval. Some of these elements are shown in Table 21. 3. Preparation of some of the transuranium elements. Name symbol atomic number reaction. Americium 95 23994, Pu plus 10N 24095 AM plus 0 minus 1 E. Curium Cm 96 23994, Pu plus 42 He 24296 Cm plus 10N. Californium Cf 98 24296 Cm plus 42 He 24598 Cf plus 10N. Einsteinium Es 99 23892, U plus 1510, N 25399, Es plus 70-1 E. Mendelevium MD 101 25399, Es plus 42, He 256101, MD plus 10N. Noblium No 102 24696 Cm plus 126 C 254102, No plus 410 N. Rutherfordium RF 104 24998 Cf plus 126 C 257104, RF plus 410 N. Seaborgium SG 106 20682 PB plus 5424, CR 257106, SG plus 310 N 24998 CF plus 188 O 263106, SG plus 410 N. Meitnerium MT 107 20983, Bi plus 5826, Phi 266109, MT plus 10N. Table 21. 3. Nuclear fission. Many heavier elements with smaller binding energies per nucleon can decompose into more stable elements that have intermediate mass numbers and larger binding energies per nucleon. That is, mass numbers and binding energies per nucleon that are closer to the peak of the binding energy graph near 56, see Figure 21. 3. Sometimes neutrons are also produced. This decomposition is called fission, the breaking of a large nucleus into smaller pieces. The breaking is rather random with the formation of a large number of different products. Fission usually does not occur naturally, but is induced by bombardment with neutrons. The first reported nuclear fission occurred in 1939 when 3 German scientists, Lise Meitner, Otto Hahn, and Fritz Strassmann, bombarded uranium-235 atoms with slow-moving neutrons that split the U-238 nuclei into smaller fragments that consisted of several neutrons and elements near the middle of the periodic table. Since then, fission has been observed in many other isotopes, including most actinide isotopes that have an odd number of neutrons. A typical nuclear fission reaction is shown in Figure 21. 14. A diagram is shown which has a white sphere labeled superscript 1, subscript 0, N, followed by a right-facing arrow and a large sphere composed of many smaller white and green spheres labeled superscript 235, subscript 92, U. The single sphere has impacted the larger sphere. A right-facing arrow leads from the larger sphere to a vertical dumbbell-shaped collection of the same white and green spheres labeled superscript 236, subscript 92, U, unstable nucleus. 2 right-facing arrows lead from the top and bottom of this structure to 2 new spheres that are also composed of green and white spheres and are slightly smaller than the others. The top sphere is labeled superscript 92, subscript 36, Kr, while the lower one is labeled superscript 141, subscript 56, Ba. A starburst pattern labeled energy, lies between these two spheres and has three right-facing arrows leading from it to three white spheres labeled 3, superscript 1, subscript 0, n. A balanced nuclear equation is written below the diagram and says, superscript 235, subscript 92, U plus sign, superscript 1, subscript 0, N, yield arrow, superscript 236, subscript 92, U, yield arrow, superscript 141, subscript 56, BA plus sign, superscript 92, subscript 36, KR plus sign 3, superscript 1, subscript 0, N. Figure 21. 14. When a slow neutron hits a fissionable U-235 nucleus, it is absorbed and forms an unstable U-236 nucleus. The U-236 nucleus then rapidly breaks apart into two smaller nuclei, in this case, Ba-141 and Kr-92, along with several neutrons, usually 2 or 3, and releases a very large amount of energy. Among the products of Meitner, Hahn, and Strassman's fission reaction were barium, krypton, lanthanum, and cerium, all of which have nuclei that are more stable than uranium-235. Since then, hundreds of different isotopes have been observed among the products of fissionable substances. A few of the many reactions that occur for U-235, and a graph showing the distribution of its fission products and their yields, are shown in Figure 21. 15. Similar fission reactions have been observed with other uranium isotopes, as well as with a variety of other isotopes such as those of plutonium. 5 nuclear equations and a graph are shown. The first equation is superscript 235, subscript 92, U plus sign, superscript 1, subscript 0, N, yield arrow, superscript 236, subscript 92, U, yield arrow. Superscript 90, subscript 38, SR plus sign, superscript 144, subscript 54, XE plus sign 2, superscript 1, subscript 0, N. The second equation is superscript 235, subscript 92, U plus sign, superscript 1, subscript 0, N, yield arrow, superscript 236, subscript 92, U, yield arrow. Superscript 87, subscript 35, BR plus sign, superscript 146, subscript 57, LA plus sign 3, superscript 1, subscript 0, N. The third equation is superscript 235, subscript 92, U plus sign, superscript 1, subscript 0, N, yield arrow, superscript 236, subscript 92, U, yield arrow. Superscript 97, subscript 37, RB plus sign, superscript 137, subscript 55, CS plus sign 3, superscript 1, subscript 0, N. The fourth equation is superscript 235, subscript 92, U plus sign, superscript 1, subscript 0, N, yield arrow, superscript 236, subscript 92, U, yield arrow. Superscript 137, subscript 52, TE plus sign, superscript 97, subscript 40, ZR plus sign 2, superscript 1, subscript 0, N. The fifth equation is superscript 235, subscript 92, U plus sign, superscript 1, subscript 0, N, yield arrow, superscript 236, subscript 92, U, yield arrow. Superscript 141, subscript 56, BA plus sign, superscript 92, subscript 36, KR plus sign 3, superscript 1, subscript 0, N. A graph is also shown where the y-axis is labeled fission yield, open parenthesis, percent sign, close parenthesis, and has values of 0 to 9 in increments of 1, while the x-axis is labeled mass number, and has values of 60 to 180 in increments of 20. The graph begins near point 65.0 and rises rapidly to near 92.66, then drops just as rapidly to 107.0 and remains there to point 127.0. The graph then rises again to near 132.8, then goes up and down a bit before falling to a point 153.0 and going horizontal. Figure 21. 15a. Nuclear fission of U-235 produces a range of fission products. B. The larger fission products of U-235 are typically one isotope with a mass number around 85-105, and another isotope with a mass number that is about 50% larger, that is, about 130-150. Link to learning. View this link to see a simulation of nuclear fission. A tremendous amount of energy is produced by the fission of heavy elements. For instance, when 1 mole of U-235 undergoes fission, the products weigh about 0.2 grams less than the reactants. This lost mass is converted into a very large amount of energy, about 1/8 times 10 kJ per mole of U-235. Nuclear fission reactions produce incredibly large amounts of energy compared to chemical reactions. The fission of 1 kilogram of uranium-235, for example, produces about 2.5 million times as much energy as is produced by burning 1 kilogram of coal. As described earlier, when undergoing fission, U-235 produces 2 medium-sized nuclei and 2 or 3 neutrons. These neutrons may then cause the fission of other uranium-235 atoms, which in turn provide more neutrons that can cause fission of even more nuclei, and so on. If this occurs, we have a nuclear chain reaction. See Figure 21.16. On the other hand, if too many neutrons escape the bulk material without interacting with a nucleus, then no chain reaction will occur. A diagram is shown which has a white sphere labeled superscript 1, subscript 0, n, followed by a right-facing arrow and a large sphere composed of many smaller white and green spheres labeled superscript 235, subscript 92, u. The single sphere has impacted the larger sphere. A right-facing arrow leads from the larger sphere to a pair of smaller spheres which are collections of the same white and green spheres. The upper of these two images is labeled superscript 93, subscript 36, Kr, while the lower of the two is labeled superscript 142, subscript 56, Ba. A starburst pattern labeled energy lies between these two spheres and has 3 right-facing arrows leading from it to 3 white spheres labeled superscript 1, subscript 0, n. An equation below this portion of the diagram reads superscript 235, subscript 92, u plus sign, superscript 1, subscript 0, n yield arrow, superscript 140, subscript 56, Ba plus sign, superscript 90, subscript 36, Kr plus sign 3, superscript 1, subscript 0, n. A right-facing arrow leads from each of these white spheres to 3 larger spheres, each composed of many smaller green and white spheres and labeled from top to bottom as a superscript 235, subscript 92, u, b, superscript 235, subscript 92, u, and c, superscript 235, subscript 92, u. Each of these spheres is followed by a right-facing arrow, which points to a pair of smaller spheres composed of the same green and white spheres, with starburst patterns in between each pair labeled energy. The spheres of the top pair are labeled from top to bottom, superscript 96, subscript 37, Rb, and superscript 137, subscript 55, Cs. The spheres of the middle pair are labeled from top to bottom, superscript 90, subscript 38, Sr, and superscript 144, subscript 54, Xe. The spheres of the bottom pair are labeled from top to bottom, superscript 87, subscript 35, Br, and superscript 146, subscript 57, La. Each pair of spheres is followed by 3 right-facing arrows leading to 3 white spheres labeled superscript 1, subscript 0, n. Below the diagram are 3 nuclear equations. Equation A reads superscript 235, subscript 92 U plus sign superscript 1 subscript 0 N yield arrow superscript 96 subscript 37 RB plus sign superscript 137 subscript 55 CS plus sign 3 superscript 1 subscript 0 N. Equation B reads superscript 235 subscript 92 U plus sign superscript 1 subscript 0 N yield arrow superscript 90 subscript 38 SR plus sign superscript 144 subscript 54 XE plus sign 2 superscript 1 subscript 0 N. Equation C reads superscript 235 subscript 92 U plus sign superscript 1 subscript 0 N yield arrow superscript 87 subscript 35 BR plus sign superscript 146 subscript 57 LA plus sign 3 superscript 1 subscript 0 N. Figure 21. 16. The fission of a large nucleus, such as U-235, produces 2 or 3 neutrons, each of which is capable of causing fission of another nucleus by the reactions shown. If this process continues, a nuclear chain reaction occurs. Material that can sustain a nuclear fission chain reaction is said to be fissile or fissionable. Technically, fissile material can undergo fission with neutrons of any energy, whereas fissionable material requires high-energy neutrons. Nuclear fission becomes self-sustaining when the number of neutrons produced by fission equals or exceeds the number of neutrons absorbed by splitting nuclei, plus the number that escape into the surroundings. The amount of a fissionable material that will support a self-sustaining chain reaction is a critical mass. An amount of fissionable material that cannot sustain a chain reaction is a subcritical mass. An amount of material in which there is an increasing rate of fission is known as a supercritical mass. The critical mass depends on the type of material, its purity, the temperature, the shape of the sample, and how the neutron reactions are controlled. Figure 21. 17. The images are shown and labeled A, B, and C. Image A, labeled subcritical mass, shows a blue circle background with a white sphere near the outer, top left edge of the circle. A downward, right-facing arrow indicates that the white sphere enters the circle. 7 small, yellow starbursts are drawn in the blue circle, and each has an arrow facing from it to outside the circle, in seemingly random directions. Image B, labeled critical mass, shows a blue circle background with a white sphere near the outer, top, left edge of the circle. A downward, right-facing arrow indicates that the white sphere enters the circle. 17 small, yellow starbursts are drawn in the blue circle, and each has an arrow facing from it to outside the circle, in seemingly random directions. Image C, labeled critical mass from neutron deflection, shows a blue circle background, lying in a larger purple circle, with a white sphere near the outer, top, left edge of the purple circle. A downward, right-facing arrow indicates that the white sphere enters both of the circles. 13 small, yellow starbursts are drawn in the blue circle, and each has an arrow facing from it to outside the blue circle, and a couple outside of the purple circle, in seemingly random directions. Figure 21. 17a. In a subcritical mass, the fissile material is too small and allows too many neutrons to escape the material, so a chain reaction does not occur. B. In a critical mass, a large enough number of neutrons in the fissile material induce fission to create a chain reaction. An atomic bomb, figure 21. 18, contains several pounds of fissionable material, 23,592 U, or 23,994 Pu, a source of neutrons, and an explosive device for compressing it quickly into a small volume. When fissionable material is in small pieces, the proportion of neutrons that escape through the relatively large surface area is great, and a chain reaction does not take place. When the small pieces of fissionable material are brought together quickly to form a body with a mass larger than the critical mass, the relative number of escaping neutrons decreases, and a chain reaction and explosion result. Two diagrams are shown, each to the left of a photo, and labeled A and B. Diagram A shows the outer casing of a bomb that has a long, tubular shape with a squared-off tail. Components in the shell show a tube with a white disc labeled detonator on the left, an orange disc with a bright yellow starburst drawn around it labeled conventional explosive in the middle, and a right-facing arrow leading to a blue disc in the nose of the bomb labeled uranium-235. A small blue cone next to the orange disc shares the label of uranium-235. A black and white photo next to this diagram shows a far-off shot of a rising cloud over a landscape. Diagram B shows the outer casing of a bomb that has a short, rounded shape with a squared-off tail. Components in the shell show a large orange circle labeled conventional explosive, with a series of black dots around its edge labeled detonators, and a yellow starburst behind it. White arrows face from the outer edge of the orange circle to a blue circle in the center with a yellow core. The blue circle is labeled plutonium-239, while the yellow core is labeled beryllium-polonium initiator. A black and white photo next to this diagram shows a far-off shot of a giant rising cloud over a landscape. Figure 21. 18a. The nuclear fission bomb that destroyed Hiroshima on August 6, 1945, consisted of two subcritical masses of U-235, where conventional explosives were used to fire one of the subcritical masses into the other, creating the critical mass for the nuclear explosion. B. The plutonium bomb that destroyed Nagasaki on August 9, 1945, consisted of a hollow sphere of plutonium that was rapidly compressed by conventional explosives. This led to a concentration of plutonium in the center that was greater than the critical mass necessary for the nuclear explosion. Fission reactors. Chain reactions of fissionable materials can be controlled and sustained without an explosion in a nuclear reactor. Figure 21. 19. Any nuclear reactor that produces power via the fission of uranium or plutonium by bombardment with neutrons must have at least 5 components: nuclear fuel consisting of fissionable material, a nuclear moderator, reactor coolant, control rods, and a shield and containment system. We will discuss these components in greater detail later in the section. The reactor works by separating the fissionable nuclear material such that a critical mass cannot be formed, controlling both the flux and absorption of neutrons to allow shutting down the fission reactions. In a nuclear reactor used for the production of electricity, the energy released by fission reactions is trapped as thermal energy and used to boil water and produce steam. The steam is used to turn a turbine, which powers a generator for the production of electricity. A photo labeled A and a diagram labeled B is shown. The photo is of a power plant with 2 large white domes and many buildings. The diagram shows a cylindrical container with thick walls labeled walls made of concrete and steel, and 3 main components inside. The first of these components is a pair of tall cylinders labeled steam generators that sit to either side of a shorter cylinder labeled core. Next to the core is a thin cylinder labeled pressurizer. To the left of the outer walls is a set of pistons labeled turbines that sit above a series of other equipment. Figure 21. 19a. The Diablo Canyon Nuclear Power Plant near San Luis Obispo is the only nuclear power plant currently in operation in California. The domes are the containment structures for the nuclear reactors, and the brown building houses the turbine where electricity is generated. Ocean water is used for cooling. B. The Diablo Canyon uses a pressurized water reactor, one of a few different fission reactor designs in use around the world, to produce electricity. Energy from the nuclear fission reactions in the core heats water in a closed, pressurized system. Heat from this system produces steam that drives a turbine, which in turn produces electricity. Credit A. Modification of work by Michael L. Baird. Credit B. Modification of work by the Nuclear Regulatory Commission. Nuclear fuels. Nuclear fuel consists of a fissionable isotope, such as uranium-235, which must be present in sufficient quantity to provide a self-sustaining chain reaction. In the United States, uranium ores contain from 0.050, 3% of the uranium oxide U3O8. The uranium in the ore is about 99.3% non-fissionable U238, with only 0.7% fissionable U235. Nuclear reactors require a fuel with a higher concentration of U235 than is found in nature. It is normally enriched to have about 5% of uranium mass as U235. At this concentration, it is not possible to achieve the supercritical mass necessary for a nuclear explosion. Uranium can be enriched by gaseous diffusion, the only method currently used in the U.S., using a gas centrifuge, or by laser separation. In the gaseous diffusion enrichment plant where U235 fuel is prepared, UF6, uranium hexafluoride, gas at low pressure moves through barriers that have holes just barely large enough for UF6 to pass through. The slightly lighter 235 UF6 molecules diffuse through the barrier slightly faster than the heavier 238 UF6 molecules. This process is repeated through hundreds of barriers, gradually increasing the concentration of 235 UF6 to the level needed by the nuclear reactor. The basis for this process, Graham's law, is described in the chapter on gases. The enriched UF6 gas is collected, cooled until it solidifies, and then taken to a fabrication facility where it is made into fuel assemblies. Each fuel assembly consists of fuel rods that contain many thimble-sized, ceramic-encased, enriched uranium, usually UO2 fuel pellets. Modern nuclear reactors may contain as many as 10 million fuel pellets. The amount of energy in each of these pellets is equal to that in almost a ton of coal or 150 gallons of oil. Nuclear moderators. Neutrons produced by nuclear reactions move too fast to cause fission. Refer back to Figure 21.17. They must first be slowed to be absorbed by the fuel and produce additional nuclear reactions. A nuclear moderator is a substance that slows the neutrons to a speed that is low enough to cause fission. Early reactors used high-purity graphite as a moderator. Modern reactors in the U.S. exclusively use heavy water, 21H2O, or light water, ordinary H2O, whereas some reactors in other countries use other materials, such as carbon dioxide, beryllium, or graphite. Reactor coolants. A nuclear reactor coolant is used to carry the heat produced by the fission reaction to an external boiler and turbine, where it is transformed into electricity. 2. Overlapping coolant loops are often used. This counteracts the transfer of radioactivity from the reactor to the primary coolant loop. All nuclear power plants in the U.S. use water as a coolant. Other coolants include molten sodium, lead, a lead-bismuth mixture, or molten salts. Control rods. Nuclear reactors use control rods, Figure 21.20, to control the fission rate of the nuclear fuel by adjusting the number of slow neutrons present to keep the rate of the chain reaction at a safe level. Control rods are made of boron, cadmium, hafnium, or other elements that are able to absorb neutrons. Boron-10, for example, absorbs neutrons by a reaction that produces lithium-7 and alpha particles. 105B plus 10 and 73 Li plus 42 He. When control rod assemblies are inserted into the fuel element in the reactor core, they absorb a larger fraction of the slow neutrons, thereby slowing the rate of the fission reaction and decreasing the power produced. Conversely, if the control rods are removed, fewer neutrons are absorbed, and the fission rate and energy production increase. In an emergency, the chain reaction can be shut down by fully inserting all of the control rods into the nuclear core between the fuel rods. Two diagrams are shown and labeled A and B. Diagram A shows a cutaway view of a vertical tube with a flat, horizontal plate near the bottom that connects to a series of vertical pipes lined up next to one another and labeled fuel rods. A second horizontal plate labeled grid lies at the top of the pipes, and a second set of thinner, vertical pipes, labeled control rods, leads from this plate to the top of the container. The walls of the container are labeled steel pressure vessel. A blue, right-facing arrow leads from an entry point in the left side of the container and is followed by a second, down-facing blue arrow and a curved, right-facing arrow that trace along the outer, bottom edge of the container. A blue and red arrow follows these and faces up the right side of the container to an exit near the right face where a red, right-facing arrow leads out. Diagram B is a cutaway image of a vertical, rectangular, three-dimensional set of vertical pipes. The pipes are labeled fuel rods and are inserted into an upper and lower horizontal plate labeled grid. Four thin rods extend above the pipes and are labeled control rods. Figure 21. 20. The nuclear reactor core shown in A contains the fuel and control rod assembly shown in B. Credit. Modification of work by E. Generalic http glossary periodny com glossary php n equals control plus rod shield and containment system. During its operation, a nuclear reactor produces neutrons and other radiation. Even when shut down, the decay products are radioactive. In addition, an operating reactor is thermally very hot, and high pressures result from the circulation of water or another coolant through it. Thus, a reactor must withstand high temperatures and pressures, and must protect operating personnel from the radiation. Reactors are equipped with a containment system, or shield, that consists of three parts. The reactor vessel, a steel shell that is 320 centimeters thick and with the moderator, absorbs much of the radiation produced by the reactor. A main shield of 1-3 meters of high-density concrete. A personnel shield of lighter materials that protects operators from gamma rays and X-rays. In addition, reactors are often covered with a steel or concrete dome that is designed to contain any radioactive materials might be released by a reactor accident. Link to learning. Click here to watch a 3-minute video from the Nuclear Energy Institute on how nuclear reactors work. Nuclear power plants are designed in such a way that they cannot form a supercritical mass of fissionable material, and therefore cannot create a nuclear explosion. But as history has shown, failures of systems and safeguards can cause catastrophic accidents, including chemical explosions and nuclear meltdowns, damage to the reactor core from overheating. The following chemistry and everyday life feature explores 3 infamous meltdown incidents. Chemistry in everyday life. Nuclear accidents. The importance of cooling and containment are amply illustrated by 3 major accidents that occurred with the nuclear reactors at nuclear power generating stations in the United States, 3 Mile Island, the former Soviet Union, Chernobyl, and Japan, Fukushima. In March 1979, the cooling system of the Unit 2 reactor at 3 Mile Island Nuclear Generating Station in Pennsylvania failed, and the cooling water spilled from the reactor onto the floor of the containment building. After the pumps stopped, the reactors overheated due to the high radioactive decay heat produced in the first few days after the nuclear reactor shut down. The temperature of the core climbed to at least 2200 degrees C, and the upper portion of the core began to melt. In addition, the zirconium alloy cladding of the fuel rods began to react with steam and produced hydrogen. Zr letter 1d460 plus 2H2 letter 1d454 Zr O2 letter 1d460 plus 2H2 letter 1d454. The hydrogen accumulated in the confinement building, and it was feared that there was danger of an explosion of the mixture of hydrogen and air in the building. Consequently, hydrogen gas and radioactive gases, primarily krypton and xenon, were vented from the building, Within a week, cooling water circulation was restored and the core began to cool. The plant was closed for nearly 10 years during the cleanup process. Although zero discharge of radioactive material is desirable, the discharge of radioactive krypton and xenon, such as occurred at the 3 Mile Island plant, is among the most tolerable. These gases readily disperse in the atmosphere and thus do not produce highly radioactive areas. Moreover, they are noble gases and are not incorporated into plant and animal matter in the food chain. Effectively, none of the heavy elements of the core of the reactor were released into the environment, and no cleanup of the area outside of the containment building was necessary. Figure 21. 21. Two photos, labeled A and B, are shown. Photo A is an aerial view of a nuclear power plant. Photo B shows a small group of men walking through a room filled with electronics. Figure 21. 21a. In this 2010 photo of 3 Mile Island, the remaining structures from the damaged Unit 2 reactor are seen on the left, whereas the separate Unit 1 reactor, unaffected by the accident, continues generating power to this day, right. B. President Jimmy Carter visited the Unit 2 control room a few days after the accident in 1979. Another major nuclear accident involving a reactor occurred in April 1986 at the Chernobyl nuclear power plant in Ukraine, which was still a part of the former Soviet Union. While operating at low power during an unauthorized experiment with some of its safety devices shut off, one of the reactors at the plant became unstable. Its chain reaction became uncontrollable and increased to a level far beyond what the reactor was designed for. The steam pressure in the reactor rose to between 100 and 500 times the full power pressure and ruptured the reactor. Because the reactor was not enclosed in a containment building, a large amount of radioactive material spewed out, and additional fission products were released, as the graphite carbon moderator of the core ignited and burned. The fire was controlled, but over 200 plant workers and firefighters developed acute radiation sickness, and at least 32 soon died from the effects of the radiation. It is predicted that about 4,000 more deaths will occur among emergency workers and former Chernobyl residents from radiation-induced cancer and leukemia. The reactor has since been encapsulated in steel and concrete, a now decaying structure known as the sarcophagus. Almost 30 years later, significant radiation problems still persist in the area, and Chernobyl largely remains a wasteland. In 2011, the Fukushima Daiichi nuclear power plant in Japan was badly damaged by a 9.0 magnitude earthquake and resulting tsunami. 3 reactors up and running at the time were shut down automatically, and emergency generators came online to power electronics and coolant systems. However, the tsunami quickly flooded the emergency generators and cut power to the pumps that circulated coolant water through the reactors. High-temperature steam in the reactors reacted with zirconium alloy to produce hydrogen gas. The gas escaped into the containment building, and the mixture of hydrogen and air exploded. Radioactive material was released from the containment vessels as the result of deliberate venting to reduce the hydrogen pressure, deliberate discharge of coolant water into the sea, and accidental or uncontrolled events. An evacuation zone around the damaged plant extended over 4 miles away, and an estimated 200,000 people were evacuated from the area. All 48 of Japan's nuclear power plants were subsequently shut down, remaining shuttered as of December 2014. Since the disaster, public opinion has shifted from largely favoring to largely opposing increasing the use of nuclear power plants, and a restart of Japan's atomic energy program is still stalled. Figure 21. 22. A photo and a map, labeled A and B, respectively, are shown. Photo A shows a man in a body-covering safety suit working near a series of blue, plastic-coated containers. Map B shows a section of land with the ocean on each side. Near the upper right side of the land is a small red dot, labeled greater than 12.5 mR/HR, that is surrounded by a zone of orange that extends in the upper left direction labeled 2.17-12.5 mR/HR. The orange is surrounded by an outline of yellow labeled 119-217 mR/HR and a wider outline of green labeled 0.25-119 mR/HR. A large area of light blue labeled 03-025 mR/HR surrounds the green area and extends to the lower middle of the map. A large section of the lower middle and left of the land is covered by dark blue, labeled less than 0.3 mR/HR. Figure 21. 22a. After the accident, contaminated waste had to be removed, and b. An evacuation zone was set up around the plant in areas that received heavy doses of radioactive fallout. Credit A. Modification of work by Live Action Hero/Flickr. The energy produced by a reactor, fueled with enriched uranium, results from the fission of uranium, as well as from the fission of plutonium produced as the reactor operates. As discussed previously, the plutonium forms from the combination of neutrons and the uranium in the fuel. In any nuclear reactor, only about 0.1% of the mass of the fuel is converted into energy. The other 99.9% remains in the fuel rods as fission products and unused fuel. All of the fission products absorb neutrons, and after a period of several months to a few years, depending on the reactor, the fission products must be removed by changing the fuel rods. Otherwise, the concentration of these fission products would increase and absorb more neutrons until the reactor could no longer operate. Spent fuel rods contain a variety of products, consisting of unstable nuclei ranging in atomic number from 25 to 60, some transuranium elements, including plutonium and americium, and unreacted uranium isotopes. The unstable nuclei and the transuranium isotopes give the spent fuel a dangerously high level of radioactivity. The long-lived isotopes require thousands of years to decay to a safe level. The ultimate fate of the nuclear reactor as a significant source of energy in the United States probably rests on whether or not a politically and scientifically satisfactory technique for processing and storing the components of spent fuel rods can be developed. Link to learning. Explore the information in this link to learn about the approaches to nuclear waste management, nuclear fusion and fusion reactors. The process of converting very light nuclei into heavier nuclei is also accompanied by the conversion of mass into large amounts of energy, a process called fusion. The principal source of energy in the Sun is a net fusion reaction in which 4 hydrogen nuclei fuse and produce 1 helium nucleus and 2 positrons. This is a net reaction of a more complicated series of events. 411H42, He plus 20 plus 1 E plus. A helium nucleus has a mass that is 0.7% less than that of 4 hydrogen nuclei. This lost mass is converted into energy during the fusion. This reaction produces about 3.6 times 1011 kJ of energy per mole of 42 He produced. This is somewhat larger than the energy produced by the nuclear fission of 1 mole of U-235, 1.8 times 1010 kJ, and over 3 million times larger than the energy produced by the chemical combustion of 1 mole of octane, 5471 kJ. It has been determined that the nuclei of the heavy isotopes of hydrogen, a deuteron, 21H, and a triton, 31H, undergo fusion at extremely high temperatures, thermonuclear fusion. They form a helium nucleus and a neutron, 21H plus 31H42, He plus 10N. This change proceeds with a mass loss of 0.188 AMU, corresponding to the release of 1.69 times 109 kilojoules per mole of 42 He formed. The very high temperature is necessary to give the nuclei enough kinetic energy to overcome the very strong repulsive forces resulting from the positive charges on their nuclei, so they can collide. Useful fusion reactions require very high temperatures for their initiation, about 15 million K or more. At these temperatures, all molecules dissociate into atoms, and the atoms ionize, forming plasma. These conditions occur in an extremely large number of locations throughout the universe. Stars are powered by fusion. Humans have already figured out how to create temperatures high enough to achieve fusion on a large scale in thermonuclear weapons. A thermonuclear weapon, such as a hydrogen bomb, contains a nuclear fission bomb that, when exploded, gives off enough energy to produce the extremely high temperatures necessary for fusion to occur. Another much more beneficial way to create fusion reactions is in a fusion reactor, a nuclear reactor in which fusion reactions of light nuclei are controlled. Because no solid materials are stable at such high temperatures, mechanical devices cannot contain the plasma in which fusion reactions occur. Two techniques to contain plasma at the density and temperature necessary for a fusion reaction are currently the focus of intensive research efforts: containment by a magnetic field and by the use of focused laser beams. Figure 21. 23. A number of large projects are working to attain one of the biggest goals in science: getting hydrogen fuel to ignite and produce more energy than the amount supplied to achieve the extremely high temperatures and pressures that are required for fusion. At the time of this writing, there are no self-sustaining fusion reactors operating in the world, although small-scale controlled fusion reactions have been run for very brief periods. Two photos are shown and labeled A and B. Photo A shows a model of the ITER reactor made up of colorful components. Photo B shows a close-up view of the end of a long, mechanical arm made up of many metal components. Figure 21. 23. A. This model is of the International Thermonuclear Experimental Reactor, ITER reactor, currently under construction in the south of France with an expected completion date of 2027. The ITER will be the world's largest experimental tokamak nuclear fusion reactor, with a goal of achieving large-scale sustained energy production. B. In 2012, the National Ignition Facility at Lawrence Livermore National Laboratory briefly produced over 500 billion watts, 500 terawatts, or 500 TW of peak power, and delivered 1,850,000 joules, 1.85 mJ of energy, the largest laser energy ever produced, and 1,000 times the power usage of the entire United States in any given moment. Although lasting only a few billionths of a second, the 192 lasers attained the conditions needed for nuclear fusion ignition. This image shows the target prior to the laser shot. Credit A. Modification of work by Stefan Mosel. Learning objectives. By the end of this section, you will be able to list common applications of radioactive isotopes. Radioactive isotopes have the same chemical properties as stable isotopes of the same element, but they emit radiation, which can be detected. If we replace one or more atom S with radioisotope S in a compound, we can track them by monitoring their radioactive emissions. This type of compound is called a radioactive tracer or radioactive label. Radioisotopes are used to follow the paths of biochemical reactions or to determine how a substance is distributed within an organism. Radioactive tracers are also used in many medical applications, including both diagnosis and treatment. They are used to measure engine wear, analyze the geological formation around oil wells, and much more. Radioimmunoassays, RIA, for example, rely on radioisotopes to detect the presence and/or concentration of certain antigens. Developed by Rosalind Sussman-Yalow and Solomon Berson in the 1950s, the technique is known for extreme sensitivity, meaning that it can detect and measure very small quantities of a substance. Prior to its discovery, most similar detection relied on large enough quantities to produce visible outcomes. RIA revolutionized and expanded entire fields of study, most notably endocrinology, and is commonly used in narcotics detection, blood bank screening, early cancer screening, hormone measurement, and allergy diagnosis. Based on her significant contribution to medicine, Yallo received a Nobel Prize, making her the second woman to be awarded the prize for medicine. Radioisotopes have revolutionized medical practice, see Appendix M, where they are used extensively. Over 10 million nuclear medicine procedures and more than 100 million nuclear medicine tests are performed annually in the United States. Four typical examples of radioactive tracers used in medicine are technetium-99, 9943 Tc, thallium-2, a 20,181 TL, iodine-131, 13,153 I, and sodium-24, 2411 Na. Damaged tissues in the heart, liver, and lungs absorb certain compounds of technetium-99 preferentially. After it is injected, the location of the technetium compound, and hence the damaged tissue, can be determined by detecting the gamma rays emitted by the Tc99 isotope. Thallium-2, 1, figure 21. 24 becomes concentrated in healthy heart tissue, so the two isotopes, Tc99 and Tl201, are used together to study heart tissue. Iodine-131 concentrates in the thyroid gland, the liver, and some parts of the brain. It can therefore be used to monitor goiter and treat thyroid conditions, such as Graves' disease, as well as liver and brain tumors. Salt solutions containing compounds of sodium-24 are injected into the bloodstream to help locate obstructions to the flow of blood. A photo is shown of two men, one walking on a treadmill with various wires connected to his torso region, and the other collecting blood pressure data from the first man. Figure 21. 24 administering thallium-2, a 1 to a patient and subsequently performing a stress test offer medical professionals an opportunity to visually analyze heart function and blood flow. Credit: modification of work by Blue Zero Cetane / Wikimedia Commons. Radioisotopes used in medicine typically have short half-lives. For example, the ubiquitous Tc99m has a half-life of 6.1 hours. This makes Tc99m essentially impossible to store and prohibitively expensive to transport, so it is made on-site instead. Hospitals and other medical facilities use Mo-99, which is primarily extracted from U-235 fission products, to generate Tc99. Mo-99 undergoes beta decay with a half-life of 66 hours, and the Tc99 is then chemically extracted, figure 21. 25. The parent nuclide Mo-99 is part of a molybdate ion, Mo-O42-. When it decays, it forms the pertechnidate ion, TcO4-. These two water-soluble ions are separated by column chromatography, with the higher charge molybdate ion adsorbing onto the alumina in the column, and the lower charge pertechnidate ion passing through the column in the solution. A few micrograms of Mo-99 can produce enough Tc99 to perform as many as 10,000 tests. A photograph and a microscopic image are shown and labeled A and B. Photo A shows a person's hand holding a graduated cylinder that contains a clear, colorless liquid, and tilting the cylinder to pour it into a vertical, cylindrical glass tube. The tube has many separate glass components and is held in place by a test tube clamp. Image B shows a multitude of tiny, red dots on a black background. The dots are collected in 4 regions and dispersed elsewhere. Figure 21. 25a. The first Tc99m generator, circa 1958, is used to separate Tc99 from Mo-99. The Mo-O42- is retained by the matrix in the column, whereas the TcO4- passes through and is collected. B. TC99 was used in the scan of the neck of a patient with Graves' disease. The scan shows the location of high concentrations of TC99. Credit, a modification of work by the Department of Energy. Credit B, modification of work by MBQ/Wikimedia Commons. Radioisotopes can also be used, typically in higher doses than as a tracer, as treatment. Radiation therapy is the use of high-energy radiation to damage the DNA of cancer cells, which kills them or keeps them from dividing, figure 21. 26. A cancer patient may receive external beam radiation therapy delivered by a machine outside the body, or internal radiation therapy, brachytherapy, from a radioactive substance that has been introduced into the body. Note that chemotherapy is similar to internal radiation therapy in that the cancer treatment is injected into the body, but differs in that chemotherapy uses chemical rather than radioactive substances to kill the cancer cells. Two diagrams are shown and labeled. A and B diagram shows a woman lying on a horizontal table with is being inserted into a dome-shaped machine. Diagram B shows a closer view of the woman's head and upper torso in the machine. A series of beams, labeled gamma rays, are shown to exit from slits in the edges of the machine, labeled radioactive cobalt, and to penetrate her head, which is labeled target. Figure 21. 26. The cartoon in A shows a cobalt-60 machine used in the treatment of cancer. The diagram in B shows how the gantry of the CO-60 machine swings through an arc, focusing radiation on the targeted region tumor and minimizing the amount of radiation that passes through nearby regions. Cobalt-60 is a synthetic radioisotope produced by the neutron activation of Co-59, which then undergoes beta decay to form Ni-60, along with the emission of gamma radiation. The overall process is 5,927, Co plus 10 and 6,027, Co 6,028, Ni plus 0 minus 1 beta plus 200 gamma. The overall decay scheme for this is shown graphically in figure 21. 27. A chart shows a horizontal line in the upper left corner labeled superscript 60 subscript 27 CO and 5272, with two arrows facing right and downward leading from it. These arrows are labeled 148M EV beta 0, 12% sign, and 031M EV beta 99, 88% sign. The upper of the two arrows points to a horizontal line, and the lower arrow points to a second horizontal line. A downward-facing arrow lies in between these two horizontal lines and is labeled 1. 1732M EV gamma. A fourth horizontal line lies at the bottom of the diagram below the second and third lines. A downward-facing arrow lies in between it and the third horizontal line. It is labeled 1. 3325M EV gamma. Below the last horizontal line is the label superscript 60 subscript 28 Ni. Figure 21. 27 Co-60 undergoes a series of radioactive decays. The gamma emissions are used for radiation therapy. Radioisotopes are used in diverse ways to study the mechanisms of chemical reactions in plants and animals. These include labeling fertilizers in studies of nutrient uptake by plants and crop growth, investigations of digestive and milk-producing processes in cows, and studies on the growth and metabolism of animals and plants. For example, the radioisotope C14 was used to elucidate the details of how photosynthesis occurs. The overall reaction is 6Co2, letter 1D454, plus 6H2, letter 1D459, C6H12O6, letter 1D460, plus 6O2, letter 1D454. But the process is much more complex, proceeding through a series of steps in which various organic compounds are produced. In studies of the pathway of this reaction, Plants were exposed to CO2 containing a high concentration of 146 C at regular intervals. The plants were analyzed to determine which organic compounds contained carbon-14 and how much of each compound was present. From the time sequence in which the compounds appeared and the amount of each present at given time intervals, scientists learned more about the pathway of the reaction. Commercial applications of radioactive materials are equally diverse. Figure 21. 28. They include determining the thickness of films and thin metal sheets by exploiting the penetration power of various types of radiation. Flaws in metals used for structural purposes can be detected using high-energy gamma rays from cobalt-60 in a fashion similar to the way X-rays are used to examine the human body. In one form of pest control, flies are controlled by sterilizing male flies with gamma radiation so that females breeding with them do not produce offspring. Many foods are preserved by radiation that kills microorganisms that cause the foods to spoil. Two photographs are shown and labeled. A and B. Photo A shows a man looking at a lighted image on the wall. Photo B shows strawberries on a conveyor belt dropping into a series of collection chambers. Figure 21. 28 common commercial uses of radiation include A. X-ray examination of luggage at an airport, and B. Preservation of food. Credit A. Modification of work by the Department of the Navy. Credit B. Modification of work by the U.S. Department of Agriculture. Americium-241, an alpha emitter with a half-life of 458 years, is used in tiny amounts in ionization-type smoke detectors. Figure 21. 29. The alpha emissions from AM-241 ionize the air between two electrode plates in the ionizing chamber. A battery supplies a potential that causes movement of the ions, thus creating a small electric current. When smoke enters the chamber, the movement of the ions is impeded, reducing the conductivity of the air. This causes a marked drop in the current, triggering an alarm. A photograph and a diagram are shown. The photograph shows the interior of a smoke detector. A circular piece of plastic in the lower section of the detector is labeled alarm, while a metal disc in the top left of the photo is labeled ionization chamber. A battery is on the top right of the detector. The diagram shows an expanded view of the ionization chamber. Inside of the cylindrical casing are two horizontal, circular plates labeled metal plates. The top is labeled with a positive sign and the bottom with a negative sign. Wires are shown connected to the plates and the terminals of a battery on the exterior of the chamber. A disc in the bottom of the chamber is labeled americium source, and 4 arrows, labeled alpha particles, face vertically from this disc, through a hole in the negative plate and into the upper space of the chamber. 2 molecules with positive signs, made up of 2 blue spheres, and 2 molecules with positive signs, made up of 2 red spheres, are in this space, as well as 2 yellow spheres labeled with negative signs and arrows facing downward. 11 white dots surround 2 of the molecules on the right of the image and are labeled smoke particles. Above the left side of the image is the phrase, "No smoke, charged particles complete the circuit," while a phrase above the right side of the image states, "Smoke uncharges the particles, circuit is broken, alarm is triggered." Figure 21. 29. Inside a smoke detector, AM-241 emits alpha particles that ionize the air, creating a small electric current. During a fire, smoke particles impede the flow of ions, reducing the current and triggering an alarm. Credit A. Modification of work by Muffet/Wikimedia Commons. Learning objectives. By the end of this section, you will be able to describe the biological impact of ionizing radiation, define units for measuring radiation exposure, explain the operation of common tools for detecting radioactivity, list common sources of radiation exposure in the U.S. The increased use of radioisotopes has led to increased concerns over the effects of these materials on biological systems, such as humans. All radioactive nuclides emit high-energy particles or electromagnetic waves. When this radiation encounters living cells, it can cause heating, break chemical bonds, or ionize molecules. The most serious biological damage results when these radioactive emissions fragment or ionize molecules. For example, alpha and beta particles emitted from nuclear decay reactions possess much higher energies than ordinary chemical bond energies. When these particles strike and penetrate matter, they produce ions and molecular fragments that are extremely reactive. The damage this does to biomolecules in living organisms can cause serious malfunctions in normal cell processes, taxing the organism's repair mechanisms and possibly causing illness or even death. Figure 21:30. A diagram is shown which has a white sphere followed by a right-facing arrow and a large sphere composed of many smaller white and green spheres. The single sphere has impacted the larger sphere. A right-facing arrow leads from the larger sphere to a pair of smaller spheres which are collections of the same white and green spheres. A starburst pattern lies between these two spheres and has 3 right-facing arrows leading from it to 2 white spheres and a circle full of 10 smaller, peach-colored circles with purple dots in their centers. An arrow leads downward from this circle to a box that contains a helical shape with a starburst near its top left side and is labeled D in a damage. A right-facing arrow leads from this circle to a second circle, with 9 smaller, peach-colored circles with purple dots in their centers and 1 fully purple small circle labeled cancer cell. A right-facing arrow leads to a final circle, this time full of the purple cells, that is labeled tumor. Figure 21:30. Radiation can harm biological systems by damaging the DNA of cells. If this damage is not properly repaired, the cells may divide in an uncontrolled manner and cause cancer. Ionizing and non-ionizing radiation. There is a large difference in the magnitude of the biological effects of non-ionizing radiation, for example, light and microwaves, and ionizing radiation, emissions energetic enough to knock electrons out of molecules, for example, alpha and beta particles, gamma rays, X-rays, and high-energy ultraviolet radiation. Figure 21:31. A diagram has 2 vertical sections. The upper section has 2 right-facing horizontal arrows labeled increasing energy, E, and increasing frequency, rho symbol, respectively. A left-facing horizontal arrow lies below the first 2 and is labeled increasing wavelength, lambda symbol. Beginning on the left side of the diagram, a horizontal, sinusoidal line begins and moves across the diagram to the far right, becoming increasingly more compact. The lower section of the diagram has a double-ended horizontal arrow along its top, with the left end drawn in red and labeled non-ionizing, and the right end drawn in green and labeled ionizing. Below this is a set of terms, read from left to right as broadcast and wireless radio, microwave, terahertz, infrared, visible light, ultraviolet, X-ray, and gamma. 4 columns lie below this row of terms. The first contains the phrases non-thermal and induces low currents, while the second reads thermal and induces high currents, heating. The third contains the phrases optical and excites electrons, photo-chemical effects, while the fourth reads broken bonds and damages DNA. A series of terms lie below these columns are read from left to right: static field, power line, AM radio, FM radio, microwave oven, heat lamp, tanning booth, and medical X-rays. Figure 21:31. Lower frequency, lower energy electromagnetic radiation is non-ionizing, and higher frequency, higher energy electromagnetic radiation is ionizing. Energy absorbed from non-ionizing radiation speeds up the movement of atoms and molecules, which is equivalent to heating the sample. Although biological systems are sensitive to heat, as we might know from touching a hot stove or spending a day at the beach in the sun. A large amount of non-ionizing radiation is necessary before dangerous levels are reached. Ionizing radiation, however, may cause much more severe damage by breaking bonds or removing electrons in biological molecules, disrupting their structure and function. The damage can also be done indirectly, by first ionizing H2O, the most abundant molecule in living organisms, which forms a H2O plus ion that reacts with water, forming a hydronium ion and a hydroxyl radical. This image shows a reaction. It starts with H subscript 2O plus radiation. There is a right-facing arrow which points to H subscript 2O superscript positive sign plus H subscript 2O. From the arrow, there is another arrow that curves upward and points to an E superscript negative sign. After the second H subscript 2O, there is another right-facing arrow which points to H subscript 3O superscript positive sign plus OH superscript negative sign. Because the hydroxyl radical has an unpaired electron, it is highly reactive. This is true of any substance with unpaired electrons, known as a free radical. This hydroxyl radical can react with all kinds of biological molecules, DNA, proteins, enzymes, and so on, causing damage to the molecules and disrupting physiological processes. Examples of direct and indirect damage are shown in Figure 21. 32. Two pairs of images are shown and labeled A and B. In the first pair, a helical structure on the left with a starburst on it middle right side is connected by a right-facing arrow to a sphere composed of smaller green and white spheres. A squiggly arrow points toward the sphere from the upper left, and a downward-facing arrow leads away from the sphere to a small circle with a negative sign. In the second pair of images, a squiggly arrow leads to a water molecule, while a downward-facing arrow leads away from it to a small circle with a negative charge written on it. A helical shape with a starburst on its middle right side is drawn to the far right, and an upward-facing arrow leads to it from the following equation: H subscript 2 O plus sign radiation yield arrow H subscript 2 O superscript plus sign E superscript negative sign down-facing arrow H subscript 2 O superscript plus sign H subscript 2 O right-facing arrow H subscript 3 O superscript plus sign OH superscript negative sign. Below this equation is the phrase indirect effect. Figure 21. 32 ionizing radiation can A. directly damage a biomolecule by ionizing it or breaking its bonds, or B. create an H2O plus ion, which reacts with H2O to form a hydroxyl radical, which in turn reacts with the biomolecule, causing damage indirectly. Biological effects of exposure to radiation. Radiation can harm either the whole body, somatic damage, or eggs and sperm, genetic damage. Its effects are more pronounced in cells that reproduce rapidly, such as the stomach lining, hair follicles, bone marrow, and embryos. This is why patients undergoing radiation therapy often feel nauseous or sick to their stomach, lose hair, have bone aches, and so on, and why particular care must be taken when undergoing radiation therapy during pregnancy. Different types of radiation have differing abilities to pass through material. Figure 21. 33. A very thin barrier, such as a sheet or two of paper, or the top layer of skin cells, usually stops alpha particles. Because of this, alpha particle sources are usually not dangerous if outside the body, but are quite hazardous if ingested or inhaled. See the chemistry in everyday life feature on radon exposure. Beta particles will pass through a hand or a thin layer of material like paper or wood, but are stopped by a thin layer of metal. Gamma radiation is very penetrating and can pass through a thick layer of most materials. Some high-energy gamma radiation is able to pass through a few feet of concrete. Certain dense, high atomic number elements, such as lead, can effectively attenuate gamma radiation with thinner material and are used for shielding. The ability of various kinds of emissions to cause ionization varies greatly, and some particles have almost no tendency to produce ionization. Alpha particles have about twice the ionizing power of fast-moving neutrons, about 10 times that of beta particles, and about 20 times that of gamma rays and X-rays. A diagram shows 4 particles in a vertical column on the left, followed by an upright sheet of paper, a person's hand, an upright sheet of metal, a glass of water, a thick block of concrete, and an upright, thick piece of lead. The top particle listed is made up of 2 white spheres and 2 green spheres that are labeled with positive signs, and is labeled alpha. A right-facing arrow leads from this to the paper. The second particle is a red sphere labeled beta, and is followed by a right-facing arrow that passes through the paper and stops at the hand. The third particle is a white sphere labeled neutron, and is followed by a right-facing arrow that passes through the paper, hand, and metal, but is stopped at the glass of water. The fourth particle is shown by a squiggly arrow, and it passes through all of the substances but stops at the lead. Terms at the bottom read from left to right: paper, metal, water, concrete, and lead. Figure 21.33. The ability of different types of radiation to pass through material is shown. From least to most penetrating, they are alpha, beta, neutron, gamma. Chemistry in everyday life. Radon exposure. For many people, one of the largest sources of exposure to radiation is from radon gas, Rn-222. Radon is an alpha emitter with a half-life of 382 days. It is one of the products of the radioactive decay series of U-238, figure 21.9, which is found in trace amounts in soil and rocks. The radon gas that is produced slowly escapes from the ground and gradually seeps into homes and other structures above. Since it is about 8 times more dense than air, radon gas accumulates in basements and lower floors and slowly diffuses throughout buildings, figure 21.34. A cutaway image of the side of a house and 4 layers of the ground it rests on is shown, as well as a second cutaway image of a person's head and chest cavity. The house is shown with a restroom on the second floor and a basement with a water heater as the first floor. Green arrows lead from the lowest ground layer, labeled radon in groundwater, from the third ground layer, labeled bedrock and fractured bedrock, from the second layer, labeled radon in well water, and from the top layer, labeled radon in soil to the inside of the basement area. In the smaller image of the torso, a green arrow is shown to enter the person's nasal passage and travel to the lungs. This is labeled inhalation of radon decay products. A small coiled helical structure next to the torso is labeled alpha particle on one section where it has a starburst pattern and radiation damage to DNA on another segment. Figure 21.34. Radon-222 seeps into houses and other buildings from rocks that contain uranium-238, a radon emitter. The radon enters through cracks in concrete foundations and basement floors, stone or porous cinderblock foundations, and openings for water and gas pipes. Radon is found in buildings across the country, with amounts depending on where you live. The average concentration of radon inside houses in the U.S., 125 pCIL, is about 3 times the levels found in outside air, and about 1 in 6 houses have radon levels high enough that remediation efforts to reduce the radon concentration are recommended. Exposure to radon increases one's risk of getting cancer, especially lung cancer, and high radon levels can be as bad for health as smoking a carton of cigarettes a day. Radon is the #1 cause of lung cancer in non-smokers and the second leading cause of lung cancer overall. Radon exposure is believed to cause over 20,000 deaths in the U.S. per year. Measuring radiation exposure. Several different devices are used to detect and measure radiation, including Geiger counters, scintillation counters, scintillators, and radiation dosimeters, figure 21. 35. Probably the best-known radiation instrument, the Geiger counter, also called the Geiger-Müller counter, detects and measures radiation. Radiation causes the ionization of the gas in a Geiger-Müller tube. The rate of ionization is proportional to the amount of radiation. A scintillation counter contains a scintillator, a material that emits light, luminesces, when excited by ionizing radiation, and a sensor that converts the light into an electric signal. Radiation dosimeters also measure ionizing radiation and are often used to determine personal radiation exposure. Commonly used types are electronic, film badge, thermoluminescent, and quartz fiber dosimeters. 3 photographs are shown and labeled A, B, and C. Photo A shows a Geiger counter sitting on a table. It is made up of a metal box with a readout screen and a wire leading away from the box connected to a sensor wand. Photograph B shows a collection of tall and short vertical tubes arranged in a grouping, while photograph C shows a person's hand holding a small machine with a digital readout while standing on the edge of a roadway. Figure 21. 35 devices such as A. Geiger counters, B. scintillators, and C. dosimeters can be used to measure radiation. Credit C. Modification of work by Osamu/Wikimedia Commons. A variety of units are used to measure various aspects of radiation. Figure 21. 36. The SI unit for rate of radioactive decay is the Becquerel BQ, with 1 BQ equals 1 disintegration per second. The Curie CI and millicurie MCI are much larger units and are frequently used in medicine. 1 Curie equals 1 CI equals 3. 7 times 10 disintegrations per second. The SI unit for measuring radiation dose is the Gray J, with 1 J equals 1 J of energy absorbed per kilogram of tissue. In medical applications, the radiation absorbed dose rad is more often used. 1 rad equals 0. 1 J, 1 rad results in the absorption of 0. 1 J/kg of tissue. The SI unit measuring tissue damage caused by radiation is the Sievert SV. This takes into account both the energy and the biological effects of the type of radiation involved in the radiation dose. The Röntgen equivalent for man, REM, is the unit for radiation damage that is used most frequently in medicine. 100 REM equals 1 SV. Note that the tissue damage units REM or SV includes the energy of the radiation dose, rad or J, along with a biological factor referred to as the RBE, for relative biological effectiveness. That is an approximate measure of the relative damage done by the radiation. These are related by number of REMs equals RBE times number of rads, with RBE approximately 10 for alpha radiation, 2 plus for protons and neutrons, and 1 for beta and gamma radiation. 2 images are shown. The first, labeled rate of radioactive decay measured in becquerels or curies, shows a red sphere with 10 red squiggly arrows facing away from it in a 360-degree circle. The second image shows the head and torso of a woman wearing medical scrubs with a badge on her chest. The caption to the badge reads, "Film badge or dosimeter measures tissue damage exposure in REMs or sieverts," while a phrase under this image states, "Absorbed dose measured in grays or rads." Figure 21. 36 different units are used to measure the rate of emission from a radioactive source, the energy that is absorbed from the source, and the amount of damage the absorbed radiation does. Units of radiation measurement. Table 21. 4 summarizes the units used for measuring radiation. Units used for measuring radiation. Measurement purpose unit quantity, measured description. Activity of source Becquerel, BQ. Radioactive decays or emissions amount of sample that undergoes 1 decay second. Curie CI, amount of sample that undergoes 3. 7 times 10 decays second. Absorbed dose Gray, J energy absorbed per kg of tissue, 1 J equals 1 J/kg tissue. Radiation absorbed dose, rad. 1 rad equals 0. 1 J/kg tissue. Biologically effective dose sievert. SV tissue damage, SV equals RBE times J. Röntgen equivalent for man. Rem equals RBE times rad. Table 21. 4. Example 21. 8. Amount of radiation. Cobalt 60, T12 equals 526 Y. Is used in cancer therapy since the gamma rays it emits can be focused in small areas where the cancer is located. A 5G sample of Co60 is available for cancer treatment. A. What is its activity in BQ? B. What is its activity in CI? Solution. The activity is given by activity equals letter 1D706 letter 1D441 equals ln2 letter 1D4611/2 letter 1D441 equals ln25 26y times 5 0g equals 0 659 J of co minus 60 that decay. And to convert this to decays per second, 0 659 J times 1 Y 365 D times 1 D 24 H times 1 H 3600 S times 1 mol 59 9 G times 6 0 2 times 1023 atoms 1 mol times 1 decay 1 atom equals 2 10 times 1014 decays. Since 1 BQ equals 1 decays, the activity in becquerel BQ is 2 10 times 1014 decays times 1 BQ 1 decays equals 2 10 times 1014 BQ. B since 1 CI equals 3 7 times 1011 decays. The activity in Curie CI is 2 10 times 1014 decays times 1 CI3. 7 times 1011 decays equals 5. 7 times 102 Psi. Check your learning. Tritium is a radioactive isotope of hydrogen, T12 equals 12. 32Y, that has several uses, including self-powered lighting, in which electrons emitted in tritium radioactive decay cause phosphorus to glow. Its nucleus contains 1 proton and 2 neutrons, and the atomic mass of tritium is 3.16 AMU. What is the activity of a sample containing 1.00 mg of tritium, A in BQ and B in CI? Answer: A 356 times 1011 BQ, B 0962 CI. Effects of long-term radiation exposure on the human body. The effects of radiation depend on the type, energy, and location of the radiation source, and the length of exposure. As shown in Figure 21.37, the average person is exposed to background radiation, including cosmic rays from the sun and radon from uranium in the ground. See the Chemistry in Everyday Life feature on radon exposure. Radiation from medical exposure, including CAT scans, radioisotope tests, X-rays, and so on. And small amounts of radiation from other human activities, such as airplane flights, which are bombarded by increased numbers of cosmic rays in the upper atmosphere, radioactivity from consumer products, and a variety of radionuclides that enter our bodies when we breathe, for example, carbon-14, or through the food chain, for example, potassium-40, strontium-90, and iodine-131. A bar graph titled Radiation Doses and Regulatory Limits, open parenthesis, in milligrams, close parenthesis, is shown. The y-axis is labeled doses in milligrams and has values from 0 to 5,000 with a break between 1,000 and 5,000 to indicate a different scale to the top of the graph. The y-axis is labeled corresponding to each bar. The first bar, measured to 5,000 on the y-axis, is drawn in red and is labeled Annual Nuclear Worker Doses Limit, open parenthesis, NRC, close parenthesis. The second bar, measured to 1,000 on the y-axis, is drawn in blue and is labeled Whole Body CT, while the third bar, measured to 620 on the y-axis, is drawn in blue and is labeled average U period S period annual dose. The fourth bar, measured to 310 on the y-axis, is drawn in blue and is labeled U period S period natural background dose, while the fifth bar, measured to 100 on the y-axis and drawn in red, reads annual public dose limit, open parenthesis, NRC, close parenthesis. The sixth bar, measured to 40 on the y-axis, is drawn in blue and is labeled from your body, while the seventh bar, measured to 30 on the y-axis and drawn in blue, reads cosmic rays. The eighth bar, measured to 4 on the y-axis, is drawn in blue and is labeled safe drinking water limit, open parenthesis, EPA, close parenthesis, while the ninth bar, measured to 2.5 on the y-axis and drawn in red, reads transatlantic flight. A legend on the graph shows that red means dose limit from NRC-licensed activity, while blue means radiation doses. Figure 21.37. The total annual radiation exposure for a person in the U.S. is about 620 mrem. The various sources and their relative amounts are shown in this bar graph. Source: U.S. Nuclear Regulatory Commission. A short-term, sudden dose of a large amount of radiation can cause a wide range of health effects, from changes in blood chemistry to death. Short-term exposure to tens of rems of radiation will likely cause very noticeable symptoms or illness. A dose of about 500 rems is estimated to have a 50% probability of causing the death of the victim within 30 days of exposure. Exposure to radioactive emission has a cumulative effect on the body during a person's lifetime, which is another reason why it is important to avoid any unnecessary exposure to radiation. Health effects of short-term exposure to radiation are shown in Table 21.5. Health effects of radiation 2. Exposure, REM health effect, time to onset without treatment. 5-10 changes in blood chemistry. 50 nausea hours. 55 fatigue. 70 vomiting. 75 hair loss 2-3 weeks. 90 diarrhea. 100 hemorrhage. 400 possible death within 2 months. 1,000 destruction of intestinal lining. Internal bleeding. Death 1-2 weeks. 2,000 damage to central nervous system. Loss of consciousness. Minutes. Death hours to days. Table 21.5. It is impossible to avoid some exposure to ionizing radiation. We are constantly exposed to background radiation from a variety of natural sources, including cosmic radiation, rocks, medical procedures, consumer products, and even our own atoms. We can minimize our exposure by blocking or shielding the radiation, moving farther from the source, and limiting the time of exposure.